If you find these videos helpful, please consider supporting AddOhms and the Bald Engineer on Patreon. Hello, and welcome to a live stream. My name is James, and I'm the Bald Engineer. If you've been here before, chat, you know what's coming. If you can hear me and my audio is good, let me know the name of a component in the chat now. So Jakeev, just saw you comment about the Z80 on the trivia. Yeah, I would actually argue the Z80 was very popular. It was in the Spectrum. It was popular for CPM before the other stuff, before like Commodore and stuff got popular. And then all of the TI graphing calculators are all running Z80s, and you can still buy a Z80 today. They're like all over the place. So yeah, I'd say it didn't get as much notoriety as the 6502. But yeah, it definitely, it's big. So hello to everybody in chat. Alfredo, G Brown, Gopi Dancer, who else is here? David Boyd, yep. So you're from Indy, huh? Yeah, I grew up in Northwest Indiana, and I just actually moved from California to Chicago. So if you were around last week, I was in a little bit more of a temporary setup, and this week I am now in my new office. This isn't going to be where my lab is set up, but I am getting my office set up. So the one thing that I haven't done yet is I haven't found my sound absorbing panels yet. And so I need to get some of those installed in here to cut down on the echo, but we're just gonna have to live with that tonight because I don't know where they're at. Yeah, so what we're gonna do tonight is continue what we started last Sunday, which was a FeatherWing that has a couple of sensors on it. And so what's going on is, since I just moved into a new house, I would like to characterize different areas and rooms and different parts of the rooms by looking at the temperature, how much humidity there is, and as well as light. And then I figured sound would be interesting to check out as well, just to see, are there different parts of the house that maybe need some soundproofing or quieter. And so when I went and looked around, everything I found was a little bit on the expensive side, and they all had like accelerometers or pressure sensors. And while those would be nice to have, I didn't need a full complement. Plus, I thought it would just be fun to design something for the Adafruit Feather form factor. So that's what we're gonna be doing today. Carpet wool works fine for the echo reduction. Yep, I agree. However, I am not going to hang rugs up on my walls because I do, so for my day job, especially now, I do all of my video conferencing from here, and so I need to cut down the echo anyway. So I need something that looks a little bit nicer. But actually, I guess I could put like a 3x5 rug with a nice pattern. That would actually be kind of interesting. But anyway, I've got the sound panels. I just haven't unpacked them yet. And regarding rugs, I've actually ordered. I've got hardwood floors throughout the house, and so I've ordered rugs, but only 1 or 2 of them have actually arrived. So I don't even have rugs to put them up. So yeah. If anything, moving has shown me how much work you've put into your setup for our enjoyment. Oh man, I tell you, it was really hard to tear down the old lab because it was definitely tuned in or dialed in. I had the lighting exactly where I wanted it. Sound wasn't as good as I had wanted it, but it was. But that was mostly, I'd say, that was mostly like because of like stuff that I was doing. But since I was renting that place, I couldn't really modify the walls, which I really needed to modify. Like I needed a way to better mount my sound panels. That's why the rug idea doesn't entirely scare me off, because I sort of like that idea. That might work. So I'm not sure why Hall is inappropriate. Because what I'm trying to reduce is the echo, or I'm trying to achieve a Hall-like sound, but I think more people would understand if I said echo. So thank you, AJ. Appreciate the thanks. All right, so let me get this out of the way, and then let's get onto my. Oh, that's not what I want. Click, and let's get KiCad up and going. Oh, also, I have. Let's go grab this real quick. Okay, let me load this, and then I'll switch my computer so that you can see it. All right, so let's take a look at this. Okay, so I just submitted to, oh, there isn't a license on this one. Huh, I better fix that. I'll do that later. So I just put into GitHub the THLS SensorWing. Super creative name, I know. Stands for Temperature, Humidity, Light, Sound Sensor Wing. This is the schematic as we worked on it last week, and then after we're done today, I'll do another commit. If you'd like to go and grab that, I will put this into the chat so that you guys can go and grab that. And then that will also be, since I did that, that'll also show up in our Discord, which, by the way, if you'd like to keep the conversation going, you can head over to our to the AddOhms Discord server, where you get announcements about the streams for me, as well as stuff I find that I think is cool or interesting. So, okay, now let's open up, let's go repository, show and explore. So which version of KiCad am I running now? Well, okay, here's the thing. I thought you guys told me that 5.1.13 was out, and maybe I just don't remember. But I did go right before the stream and download. In fact, that's where I was on before I opened up GitHub. I went and downloaded 5.1.6, which I don't even remember what I was running before. And oh, also this is a different computer than what I was using last week. So anyway, yeah, so I've got 5.1.6 and I did that right before the stream, which I thought, you know, this is either going to go smooth and then nobody will notice, or anyway, so this is what happens now when I open up my schematic. Getting told that the symbols are broken and that they're trying to get rescued. Which I, you know, frankly, I don't understand what this is trying to tell me. I don't fully get it, so I always just click OK. And now we end up with all of our symbols are missing. So, and I think these are all the ones that we created, right? Because I think this one was already, excuse me, that one was already in KiCad or KiCad. And by the way, since somebody in chat did say something, I forgot who, Wayne, the project leader for KiCad, has said it is perfectly okay to call it either KiCad or KiCad. I think he says KiCad, but I'm pretty sure in that same presentation he said it both ways. So I think the more important thing, I was gonna say the more important thing, but I think the thing that has occurred is, oh, I think I know what happened. Yeah, okay, well, I don't care if you can't find that, because we're not gonna play with that tonight. So, but I think the thing, you know, it's sort of like, I think KiCad, or just by the nature of the open source community, I don't think anybody will ever agree the correct way to say it. So I try really hard to say KiCad or KiCad. And in fact, if you go back to like the AddOhms episode, when I did the 3 parts on how to design a custom Arduino board, in one of the parts, I think it might have been the second one, it was when I did the green screen with the TV behind me, or use the green screen so it looked like a TV was behind me. You can actually tell every time I say KiCad, I hesitate just a little bit because in my mind, I'm thinking about it before I say it. And so, yeah, so because I was consciously trying to change between the 2 pronunciations. So what's going on? I don't fully understand why these got lost and needed to be rescued. So I'm just going to each of these parts. I'm hitting E to open up the properties, and then I'm going down to library reference. And since we created these in the stream last week, I'm just doing a search and they're showing up in the library that I created. So I'm just replacing the names, and now we're getting the names back. So, like I said, don't fully understand why that happens, but I'm not going to get really upset about it. It generally seems like once I fix it, it doesn't break until something else happens. So, I think they should rename the KiCad project to something more sensible. Actually, you know what? Well, I'm going to spoil a trivia question, because one of the trivia questions is, what does KiCad actually stand for? And it actually doesn't have a meaning. The original founder, one of the founders of the original project, named it after his friend's company, which had Ki or Key in the name, and then he just added CAD. So there's lots of people who come up with what KiCad or KiCad means, but the person that created the name admits that it has no meaning. It's just a word. So I totally agree. Is it MacGyver? Is that how you say your name? Mac? Maybe I'll just call you Mac just in case. I actually kind of feel like well, I'm going to be two-faced about it. I think it should be renamed to something else so that it is more descriptive of what it is and you know, what it is. But on the other hand, why would you change it now, especially with the popularity that it has at the moment? Babbitt is sharing a t-shirt from Chris Gamble, which I do have somewhere. In fact, I might have even worn it to KiCad. But anywho, okay. So here's where we are on our schematic. So there was a couple of things. What was this to do? Figure out pinout to featherboard, pick 2 feathers. Okay, so we'll worry about that later. I want to look at this later. This is a note about how does the PDM microphone work. So this doesn't just put out an analog waveform, it actually puts out pulse density modulated digital data. And so I think that'll be cool to look at a scope when we get the boards back. I didn't look anything up about the micro SD, but I just copied the way that I copied the pinout that Adafruit's using, so we're gonna go with that. Excuse me. Now, the one thing we did think of last night, or the last time, was do we really want to power all of the sensors directly off of the 3.3 volts, or do we want to be able to control turning them on and off? And so I think what I want to do is, because one thing I'm gonna want to do is when we get the boards back, I want to measure the current draw of the, And so I think what we're going to do is we're going to add a 2-pin header so that I can either just short the pins out, or so I can put a current meter in series easily and figure out how much current these are drawing when we're running and when we're not. So I'm going to leave the 3.3 volt nodes everywhere else, but I'm going to actually zoom in on the feather template that we used, and we're going to I'm going to delete this node, delete this, and then we're going to copy this name with C, edit this, and we're going to call this 3.3 from feather. Feather, yeah, that's a good name. I like that. That's going to work. And then we're going to turn on music. Actually, can you guys already hear the music? That's weird. Oops. You weren't supposed to be able to hear that yet, because that's hella loud. Let's try turning that down a bit. Yeah, that was, hey, yeah, my bad. I did not mean to have the music as loud as it was. Okay, so we got that going. So then what I want to do is over here, let's add, we're going to add an MO2. So, or let's go, I thought MO2 was the universal name, but it doesn't look like it. It's con 1 by 2. All right, and then, no, I don't know why I'm doing it this way. This is open source, so we're gonna use the Freetronics one. I just really like his symbols. So let's do this, and then we're gonna go 3.3 volt to copy this one. You gotta figure out how long to make these. All right, go like this, go like this, go like that. All right, that's kind of dumb looking, isn't it? Let's move this over. Oh, I always do that. So I'm gonna hit G while I hover, and then I can just easily move that over. All right. Kind of do that. Okay, now one thing we're missing so we put decoupling caps for each of the parts. I don't know if we're going to populate it, but I am going to put a not a resistor. But I am going to put a, what we'll just say large capacitor here for decoupling directly from the board. The reason I'm not positive if I'm going to populate this one is because I'm afraid of the leakage current from a large capacitor. So surface mount capacitors are a pretty good dielectric. They don't have a lot of leakage current. That's where when they're charged up, that's the current that actually leaks. And so that's basically just wasted energy. And what happens is as you get to higher value ceramics, there's more ceramic layers. And so their leakage current goes up quite a bit. In fact, I was trying to make a regulator circuit a couple of years ago where when it was in standby, it would draw zero current. And what I found out was the decoupling capacitor that I put on the input of the regulator was drawing a couple hundred nanoamps just because of its leakage. And so that's something we'll have to think about. But I want to make sure we have pads for it in case I do want to have a decoupling cap in the final design. So we'll do that. Okay, we got that down. I'm happy with this. Oh, I know. The other thing I was thinking about with this is if we have room, I want to have a solder jumper between these two nodes. And then that way, it would be really easy to bridge the solder point versus putting in header pins and then shorting those out. So we're going to do that because that'll be fun, right? I think so. Okay. Oh my gosh, I did it again. Header pin 4-3. Oh, huh. I swore I had put a note in here to do this, and I guess I did. I just forgot about it. Okay. The other thing we're going to add, and we'll do another solder jumper for this as well, is the all-important LED. So let's put a resistor, and then let's add a lead, unlead it. What is the difference between these two? I like this one better. And then let's do this. And scene. All right. So that is that takes up a lot of space. So let's redo this. Let's move this over here. Move this over here. So I'm hitting M to move the symbols so hover over the symbol, hit M to move it, and then R while it's moving rotates. And actually, I think you can rotate. Yeah, you can rotate while it's in place. But yeah, so it just this is, to me, it's I say this often, but with KiCad, once you learn the keyboard shortcuts, it becomes super easy to use, and I think it's one of the best schematic capture utilities, just because the hotkeys or the shortcuts all work really well. All right, power LED. Let's move this one up here. Let's hover over the label, put that like right there. All right, so. Oh man, you guys tell me how to do this. G doesn't work when you do a group, so there's a different hotkey, and I forgot what it is now. Shucks. Okay, move this one to here. I'm gonna put 1K, but there's a really good chance I'm just gonna populate that with 4.7 because I don't really care how bright it is. I just wanna have an indicator, and I think if I use maybe a really good green LED, we should be able to see it. *_small always. Jacob, what do you? Oh yeah. I always like the small ones. That's because I don't know, for maybe in case somebody's not familiar. So there's a couple of different resistors. So like, okay, first there is the US version versus the international version. Even though the AddOhms logo is the US version of a resistor, when I draw schematics, I like to use the international, and it's because I have redrawn so many schematics in Adobe Illustrator that I've just gotten used to the square or the rectangle instead of the squiggly lines, but both are available. And there are big and small versions of each. And so I use the small ones because look how much space those take up. And we actually learned that trick about a year ago when we were drawing part of the Apple IIgs schematic on a live stream. Somebody in the chat was on me about using the small versions, and I will always use the small ones from now on. Okay, so we got our power LED. We've got a header for the power, or for the 3.3 volts. Have some solder jumpers. Of course, the reason I'm putting a solder jumper here is because maybe I don't want the board to always be drawing power from the LED. So this way we can easily enable or disable LEDs just with a tap of our soldering iron. Oh, you know what we haven't done? Oh man, I need this. I don't have my jokes. We haven't actually wired up anything to the feather yet. Okay. So here's what I want to do. Let me get a text box going. So we'll need SCL and SDA. Those are going to be our, oh, what'd you do that for? Those are going to be our, that's going to be our I2C symbols. So what was going on there is I kept hitting Shift Enter to go to the next line, thinking that I had to do that. But KiCad's smart enough that when you're in a text box, it doesn't take action on the thingy-mabob. So I'm going to put, so 32, okay, so those are going to be global. For the RTC, there is DS3231 reset, DS3231 int, interrupt. I'm just used to it because of Excel. And there is 32 kilohertz, which if we have pins available, we're gonna break those all out to pins because why not? For the APDS, we have an APDS interrupt, and then that has I2C, so that's good. All right, let's do this. Move this over here. E to edit that text again. Should squiggly lines for resistor be 3 or 4 peaks? So, AJ, what I have been told is that it should be, I think it's 3 peaks, and anything over 3, it means it's a heater instead of a resistor. Now, if you go look at the AddOhms, if you go and look at the AddOhms logo, I did not know that when I made this, the symbol. And so the symbol, or my logo, is actually add heaters and not AddOhms. But, oh well. Too late to fix that now. Hey Flask, how you doing? Good to see you today. We are picking up from where we left off last time. Okay, so that gets the, oh no, SHT30. All that we have there is SHT30 and an alert. Okay. Now down here, okay, we're gonna have, okay. Where did I put those? Oh, they're up here. So for the micro SD, We have SDD out, SDCS, SD clock, SD DIN. I can't tell. I think that's a capital IN. And SDCD. You know what? I think we're going to run out of pins, but that's okay. A lot of these are optional, so we'll be able to. I think we'll be okay. Now, every time. So PDM is going to be PDM clock, and PDM data. Okay. So now we've got the RTC, PDM, the light sensor, the SHT30. I think we're in good shape. Okay. Put that in your trivia. Okay. Actually, tell you what, you guys want to see some behind the scenes stuff? Let's go do that right now because I'm going to forget. So Python live trivia. So this is actually, the trivia that I run, a couple of people have actually asked me for the video of it. It's not video. It's actually a HTML based display that I just did. Like, got the computer screen with with a stock image and some CSS, and then there's a Python program running on my Pi which actually randomizes the questions and then does the web server side. And so it actually passes a JSON object with the questions and the answers over to the browser object, which that does the display of what you actually see. So it's actually a two-part program, which I guess some might say front and back or front and whatever. Anyway, so what I'm logged into now is, so I'm logged into my Pi, and then I've got a utility, which I call Live Trivia Database, where I can actually well, I can add questions. I think I can edit some of them, but not everything in here works. The biggest thing that I do is I have to reset the date that the question gets displayed, because every time it displays a question, it marks it so that I don't repeat questions until they've all been displayed. Now, there's been a couple of times, like today, I had to reset it because I accidentally left it running overnight, so it exhausted all the questions. So anyway, so let's do add entry, and the question will be, can you zoom in on the terminal? Let's see. I don't know if I can. I don't know. Is there a way to, oh, here we go. This is what I want. Let's go 16. Okay. That should make it a little bit easier to, I could go bigger. Now that I know how to do it, this is easy. Okay. So that should be a little bit easier to see now. Okay. So the new question is going to be, how many peaks does a resistor, a US resistor symbol, how many peaks does a US resistor symbol have? Schematic symbol, right? How many peaks does a US resistor schematic symbol have? How many peaks does a US resistor schematic symbol have? Okay. might be able to do control wheel to zoom. Okay, maybe I'll try that. After we do this, I don't want to mess this up. Okay, so I don't have to always put the correct answer in first, but I usually do just because in that way I can make up all the other answers. So I'm going to say 3. And that will be for the correct answer. And then we'll say 2, and that's incorrect. 4, that's incorrect. And for this last one, we'll say does not matter, and that will be incorrect. Okay, explain the answer. So now I'll explain that 3 peaks means resistor, and more than 3 means a heater. Nobody tell James about James to look at the AddOhms logo. Might be a little bit long, but I think that'll still fit. 3 peaks means resistor, and more than 3 means a heater. All right, who are you, bald engineer? URL reference. We'll skip that for now. Okay, so now it's in there. So like I was saying earlier, so here it is, 49. As I was saying earlier, there is a question for KiCad. What does the Chi in KiCad mean? Typo in symbol. Yep, okay. So that's where we just go this into here. And now it's fixed. See? Simple. So easy. Okay. Actually, I should leave it. Never mind. And then, okay, since we're on this, I know we got to get back to KiCad, but when coding, should you use spaces or tabs? For indentation? Is that how you spell that? Okay. When coding, should you use spaces or tabs for indentation? Answer, tabs, and that is the correct answer. Spaces, and that is incorrect. Explain the answer. Anyone who answered spaces will be banned. Bald engineer, URL reference. We don't need to add one for that. Okay, there we go. So, actually, yeah, that'll be fun. I'm going to leave that one in there just like that because I think every time it comes up, it's going to cause trouble. So yeah, I think that'll be a good time. Okay, so that's the trivia stuff. Let me do one thing real quick. RM star. Yeah, that's fine. Okay, and then that's so that I can catch it. That's so that I can catch it later. Okay, maybe on Sunday I'll actually take you guys through how the trivia stuff works because I'm gonna have to do a shorter stream Sunday, but maybe we'll do one on just how the trivia program works because I don't know. I think it's kind of fun. But anyway, we'll get back to KiCad now. Just type white spaces. You can't see them anyway. Typo you had asked, you meant answered? What? Did I really? Lame. Ugh, come on. What did I spaces? When coding for answer, anyone who, yep, boy, that was dumb. I was gonna put quotes around that, but I don't want to trust that. Hey, RJ, good to see you. Thanks for the correction. Should it be mean as in arithmetic, average, or many? AJ, I don't fully understand. I'm not sure I understand what your which one you're asking about. Okay, let's get back to the KiCad. One more thing. Hold on. All right. Okay. I copy, so I have that in the CGI directory, but then I copy it to my home directory because I've got my Pi's drive mapped to my computer. Then that way I can copy those files over. And the previous question. Okay. Oh my God. Did I seriously? Okay. Thanks, guys. That was a terrible. Let's go back to How mean, man, I are English good. How many peaks does a US resistor schematic symbol have? Okay, cool. Got it. All right. And here we go. Now we can get back to the real stuff. Excuse me again. So, I want to save this. So I'm going to do a screenshot of it before we go and mess it up. So micro SD card is going to be a little bit easier because we just need to grab master out, sleeve in. So SD D out. And then we're going to call this SD clock. I'm going to hit G, move that. And then we're going to call this one SDD in. G and move that. So this one, and this one are taken care of. Oh, I know one thing I was going to look into was the CD and find out how that works. Oh crap. I'll be right back. I am losing power on one of the devices I'm using to actually see what's going on. and I totally forgot to plug it into AC. So, sorry. Okay. The problem is I've lost my screen for some reason, and I need to figure out why. There we go. Okay. Whew, sorry about that. So, long story short, I don't have the cable for my spare monitor, and so I'm using my laptop with a USB capture card as my second monitor, and or USB capture device, not a card. And the battery just died, or was just about to die. So, oops. Okay, moving on. Now, I'm going to guess that whatever we select for chip select doesn't really matter. So what I'm like to do at this point is let's kind of do this and say this is going to become SD chip select. And I know what I want to do. So what I don't know is this CD switch, this is chip detect. I don't know if the way that this works is this is basically like, do these get shorted out when a card goes in, or what goes, you know, what's actually going on with them. So here's what we're going to cheat, because I don't know, I don't feel like looking up. If somebody in chat figures it out, you would be my hero. But what I'm going to do instead is just go and say, okay, maybe we just do something like this. We'll just connect them both, and then we'll figure it out later. Did you rename MOSI to SDD out? Yeah, I think I did. I might have did that. I might have done that backwards. So pin 5 is master out, slave in. So that should actually be data in. I did do that backwards. Good point. So when you're looking at a SPI device, so there's two serial signals, one going in and one coming out. And the way that they actually named it is, and this is a historical name, so, but it's master out, slave in, and then master in, slave out. And so instead of saying in and out, just or transmit or receive, this is so that you can clearly tell that the host is sending data to the device, or MISO is the device is sending to the host. So from the device perspective, and this is, I did get this backwards, the way this should work out is that data in on the device should be connected to pin 5 and data out should be connected to pin 4. But when we go look at our schematic, we'll see that I did that backwards. I said data out, right? Because this is master out, slave in, and then this is master in, slave out. Good call, Tac Z. Yeah, frankly, the only reason I wish these were named different is I'd rather them be host out, device in, instead of the other words, because, you know, reasons. So, okay. All right, so G Brown sent us this. So actually what we should do is go look at, okay, you got, so what we really should look at, because this is the one I'm going to order, since I've already got the footprint for it and we verified that it's orderable. Did I? Nope. So then let's go look this one up. So go to Octopart, put this in. So this is the, yeah, well, German words in general are difficult for me. One of my favorite things about German is how there's like no new words. Everything is just, you just keep adding words to other words to mean stuff, which has made it really difficult for me to learn how to speak it. Let's save this. And now I'm doing this. I feel like we've already done this, but that's okay. Because I want to do a, how do you edit, rotate? Well, we're just going to do it this way. Let's go to downloads, save. And then that way we can just go to the download folder and open up this and then do rotate that way. I don't know why this is getting made to be so big. It's like it must be going across both my desktops. Yeah, that's cool. I still appreciate you grabbing the other data sheet. I just, since we know the exact part that I'm going to use, it probably just makes sense to look at this one. But I feel like none push. Okay, I don't know what that means. But hey, it was checked by Jane and Henry, so that's cool. So CD switch. See, this only shows one switch pin though. Oh, okay. I do see it now. So there's this pin and then this pin and then these just get connected together. So when there's a, so we actually, what we need to do, if we connect this one to ground and connect this one to an IO pin and then just use a pull-up resistor, then we'll be able to detect it. Okay, so that's what we got to do. So one of the pins goes to ground and the other pin will go to our device, and then that way when they get connected, it'll just create a that shorts that together, and then our pull-up resistor, so we'll see high or low. I mean, whether it's normally open or not, that's sort of the don't care. I just didn't realize that this is what they were doing, is you're literally, it's the two pieces of metal. So, okay. So we'll make, that actually helps out quite a bit. That's actually going to be cool, because then we'll know when there's a card in. So we don't need this anymore. We don't even need that. We need ground. Let's just kind of put it over here so it's nice and clean. And then we'll edit this one. We'll go back to SDCD. And then I can come back over to my stuff over here. Let's delete this one, edit. Okay. And then we'll just have to do a pull, we'll use the internal pull resistor on that. Okay. So the only other one is then we have the chip select, and we'll just do that. And then we'll have all the things we need for the micro SD. Okay. So next, let's do PDM clock and data. Ah, what did you do? Might be zoomed in one level too far. Okay. Okay, got that. The other one we're going to, okay, SCL and SDA. Okay, they're already labeled, so we should be good there. And then we did put pads on this board so that we can add pull-up resistors should we need them. So what does this leave in terms of digital pins? We have 1, 2, 3. Oh, you know what okay, I just realized we're going to, let's finish this pin out. We need to do a battery measuring circuit so that we can get a sense for where the battery's at. Okay. So, but I want to get this pin out finished before we go and do that. Just do that. Just put it right in my face. Okay, so these are taken care of, so we can kill that. I feel like let's do the DS3231 RST. Int and 32K. Very unlikely we'll actually use these. We might use the interrupt, but if we've got the available pins, then I would prefer to wire them up. And if we don't have enough pins, which I guess I could just count it real quick, but yeah, because we only need 3 more. Because then we're gonna come over here. And I'm not married to these actual layout. So when we get over to the PCB and after we've moved parts around, we might have to come in and swap some of these pins around just so that things are a little bit cleaner for the layout. For now, I'm just trying to make sure that we have enough pins available that we should be good. SHT30 alert. Okay, so we got those 3, and then I did the init, or interrupt, and the alert, and then all that's left. Okay, SDA and SCL, that's like done. So, okay, so the only other battery is, the only other signal is, then I want to do bat measure. Oops. Yeah, no, that's what I wanted to do. And then we'll add one of those. So I think we should be in good shape. Okie dokie. So what does the worth datasheet? I mean, it ought to just show it as, I mean, it's probably going to look pretty similar to what the amp datasheet had, right? Uh-oh, why is that? That makes me nervous when that locks up. Yeah, okay. That doesn't make sense. That must be for the shield. Anyway, I'm with the Amphenol datasheet. I'm happy with where it's at. Okie dokie. So what we're going to do now, it's gonna be cool. We're gonna also do VUSB mesh, because then we'll be able to actually tell when the board is, oops. Then we'll be able to tell when the board is plugged into USB, and that would be cool. Okay, so I think we're going to delete these labels because we've made our own now. So let's see who's the farthest. The biggest one is going to be this one. I'll just move all of these. And now I'll use G to connect them. Although I guess I could just hit wire too. That's not too bad. Okay, so that looks good. And then looks like he's going to be the longest one. So let's move this to about here. Delete those, move this, move that, move that. I don't know if I can. How do you? There we go. Okay. Sorry for my name, it's German slang. Oh yeah, because I said I was, I've tried to learn German. Hey Rod, good to see you back. Project's going well. We're almost ready to get over to the schematic or PCB side. There's two things we're going to add though, is I want to be able to measure the voltage of the battery, and I also want to know if we're connected to USB. And so what we're going to do for that is, so USB should be 5 volts. So we're just going to do a voltage divider, and I don't really care what value the resistors are because we'll be powered, so we can waste and burn as much energy as we want. So we'll do this, put this to be about here. We'll hit G to kind of move that one up, G to move this one down. Wire to go to here, and then this will be the USB. Okay, I like that. And then we'll copy a ground, do a wire, and then we can move all this to someplace better, like right here. We'll do a little bit of text, and so to detect, let's see, USB power detection. Okay, so we got that one. And then to measure the battery voltage, we got to be a little more clever. And so what we're going to do there is we're going to use a PNP transistor, which we're going to have to go find one because I need to know what the pinout is. But let's lay out the, is there a small version of that? Now I'm addicted to the, probably not. Okay. So we're going to connect the emitter. We're going to connect the emitter to, I think they call it we called it VBAT. Okay. And then uh-oh. We actually need 2 pins. Because this is going to go to A0. I don't like this. Because we're trying to, we need a high side switch. So basically I want, I'm going to name this something else in a second, but so the idea is I want to turn on the pin. Oh wait, no, this will be okay. Yeah, this will be okay. So what we're going to do is move this over, maybe move this down, clean all this up later, but this one we need a resistor. Let's go. There we go. So we might end up using 1K just because, man, I don't like having more than one resistor value, but that's okay. Okay, so what we've got here is this is going to be this transistor is going to be a high side switch where we're connected to the battery, and then with the I/O pin of the AT Mega, we're going to turn on this transistor so that we can measure the voltage. And so normally we would actually use the internal pull-up resistor, but I don't know for certain. What we need to add is a pull-up, because I want to make sure that but then that'll allow it to sneak back through. Okay, we're just gonna have to use the internal pull-up resistors. Ooh. So internal pull-up will only go to 3.3 volt. Charged battery would be 4.2 volts. Oh, so that's a problem. So we actually do need to have a voltage divider. And if we do a voltage divider, then we should probably do a low side switch. Oh, no. Yeah, well. Hey, Jay Kittle, how you doing tonight? Okay, here's where I'm wrestling in my mind. So VBAT could be up to 4.2 volts when the batteries are fully charged, right? Since we're powering, most likely going to be hooked up to a board that is only 3.3 volt, you don't want to put 4.2 volts onto the pin, because you shouldn't exceed an input voltage on a pin higher than VCC. However, we're only going to turn it on every once in a while, so that's the whole point of this circuit. And there's going to be about a 200 millivolt drop through. Man, that's still not going to be enough. That's not enough. I feel like we should add another diode. Okay, so now what we'll end up with is, or I guess we could also just do a voltage divider. Yeah, so when the circuit's powered off, the battery will get discharged through the PNP diode and the port protection diode. Yeah, I'm trying to think through this. because what we could actually do we could actually maybe do something like this. There's probably a guide somewhere that explains exactly how to do this correctly. And then if I move this over a little bit more, and then what we could do is do a pull up to VBAT. So what I'm thinking now is this way we can use the IO pin to, nope, that won't work, will it? Because if I make this 0 volts down here, this diode won't conduct. And if I do that, then it just makes it pointless. I guess the other way we could do this is if we did it with an NPN. We did something like this. And then, so no, I think we have the same problem with this one. I've done this before, so I don't know why I'm struggling right now. I'm forgetting how to do something. Wait a minute. What if we use the PNP to turn on what if we use the NPN to turn on the PNP? And then that way, so if we did that, so if this went into here, and then this goes to here. So I'm going to rename this for the moment, just so that it's clear that this is the pin that we're controlling. So A1 is output, and then A0 will be input. So we're going to do this. So this will turn the transistor on. Hey, thanks for the follow, Eltravilo. I'll always give them a try, but I don't think I ever get anyone's name right. So we're working on a sensor board for a Adafruit Feather. This sensor board will only have temperature, humidity, light, and sound, which is why I gave it the incredibly descriptive title of THLS, temperature, humidity, light, and sound. At the moment, I'm trying to think about how can we measure the battery voltage without back-powering the microcontroller we're connected to. Because if we just connected the battery voltage directly to an analog input pin, what actually ends up happening is the entire chip will get powered by the protection diodes, and so you kind of have to. We have to figure out a way to hide the battery, and so the challenge is that the battery is going to be 3.7 to 4.2 volts, and our VCC is only going to be 3.3 volts. So one challenge is we have to step the voltage down a little bit. Not too worried about that. A diode is actually going to be good enough. But the second problem is we still can't have a path where current can leak, so to speak. So what we can do here is, okay, I think this is what I want it. David says I completely butchered his name. Yeah, you've got like, you know, unlike most names, yours has letters and vowels, and they tend to be, you know, alternating, and so they're just a little bit harder to pronounce. Just a little. Okay, I think this is what I want, because when there's no circuit power, the only thing present is VBAT, then this pull-up will hold VBAT at basically off. So there won't be a chance for 0.7 volts to develop across this this diode junction. Oh, and then what I need to do. So, okay, so let's move this, let's get this in a little bit cleaner spot, because that's kind of messy at the moment. Okay, here's what we got going on. Maybe a 3-pin regulator with less of a forward voltage drop. Well, we're going to be limited by whatever the, so we're relying on the 3.3 volts from the let me think about that for a second. So I was going to rely on the 3.3 volts from the actual wing or feather board, because all the feather boards have a 3.3 volt regulator. But since we have access to the battery pin, we could actually put our own 3.3 volt regulator on our wing with an enable, so that we could then easily turn the sensors on and off, or more easily turn the sensors on and off. I hadn't thought of that. Okay, maybe we're going to do that. I know what we're going to do. Let's figure this circuit out, because I still have to then go find the transistors for this. So let's figure this out, and then let's look at the, then let's move over to the PCB and see how much room we have. But I'm liking the idea of maybe adding we could actually do that, and then that way we could actually control when we turn the sensors on and off. I sort of like that idea. I sort of really like that idea. Can the A to D input be as high as 3.3 volts? Some limit to 2.5 analog input. Good question. Let's go look at, so I know one that's going to have trouble would be an ESP32, right? So I think those have a limited input. And then, okay, you know what? Let's just be smart about it. We don't even need the exact voltage. So let's just do a voltage divider. Instead of this silly diode. Because again, it's not like this is going to be on all the time. So yeah, this is going to burn a little bit of energy, but it's not much. Okay. Okay, so then that way the maximum that we'll ever get here is 2.1 volts, which for an what's the maximum input, analog input for an ESP32? Because I think the 8266, wasn't it limited to like 1 volt? Or I'm thinking of the analog out. AJ, I see your question. I'll get to that in just a second. So they'll read anything between 0 and 3.3. Okay. Okay. So if we cut it in half, we'll be fine, I think. Ooh, DJ, that sounds terrible. I've actually found I haven't worked with the ESP32 a lot yet, which I know I'm like the only person that hasn't. But on the 8266, the ESP12s, I found those to be really static sensitive. I have several modules that they were working fine while I was working with them, and then out of nowhere they just stopped working, and all I can think is they took a ESD shock. So, okay. Okay, so I think this is how this will work, is when there's no circuit power, there'll be no voltage here, so there's not anything to develop a 0.7 volt drop here, so this transistor will remain open. Since it will be open, then the base of this transistor will be pulled up to the battery voltage, and the emitter will also be at the battery voltage. So again, no 0.7 volt drop, so this remains open, so there's no leakage through the transistor, or minimal leakage. So then when I turn, let's see, if I put a 0 from the output pin to here, then that actually just keeps this off. And then if I turn this on with a 1, then this will start conducting, which means this path conducts, and then we'll have 0 volts here, or like 100 millivolts or whatever the CE voltage is here. And so then we'll have VBAT minus 250 millivolts, which will be enough to turn this transistor on. So we actually do need one more resistor. And then once this turns on, man, I hope these all already have, okay, good. So then once this one turns on, then this starts conducting, so then we'll get battery voltage here minus the voltage drop of that, divide it in half, because why not? And then we get the output. Okay, that's how we can measure the battery voltage without doing what's called back powering. Okay, AJ is asking, is this Darlington pair? This is not. Darlington pair is, I mean, it's a special transistor, but it actually looks more like this, right? It's something like this. Okay. I just now realized I don't actually know what a Darlington pair looks like. But it's basically, that's not how I would have drawn it. It's basically two PNP transistors, or I think you can do it, well, usually it's NPN, I'm sorry, I said it wrong. It's two NPN transistors that are basically cascaded, so you get higher gain and effectively more current. In modern designs, I don't know of any case where you actually need a Darlington. There's enough BJTs and MOSFETs with either the gain or the current that you need that this design doesn't really get used very much. I know in a lot of hobby projects, people are still using, what is it, the tip 120 or 122, but I don't really see any reason to use it anymore. It's like a quad array sometimes also used in the stepper drivers. Okay. I mean, I could see that being a more, well, I don't know what they're actually doing with it, but I could see other uses. Okay, so long story short, this is garbage, so we can get rid of that. We're gonna need a nice big spot on our schematic for our new circuit. So why don't we see if we can rearrange things a little bit. So let's move all of this stuff up. And then let's put this one over here and bring this one over. What I was thinking is something more like this. Let's put this over here. Oh, I see what I was doing. Okay, let's move this up, maybe up into this corner. And then let's try to get this one roughly to here. And then see already, I'm gonna grab the wrong one when I try to move this. So then can we fit this guy up here? Ooh, that's tight. Maybe not. Can we get this stuff to move up into here? Okay, I'm okay with that. What we're gonna do then is, let's just, because these are notes that I'm gonna delete at some point, and then let's put this, say like right here. And then I'm gonna take all of this and that stays there. And then let's move this so that it's like basically like this. Okay. And I think we can move everything over just a tad, just to make it a little cleaner. Okay, so now we opened up a bunch of space. So let's move this over to here. And then these things will move up here. This can be moved up to here. This can be moved up to, let's say, roughly there. And now we've got plenty of room for our battery voltage detection thing. And then I got to rename some of these labels. Okay, so let's move this to do like right here, just get it on my way. So this is going to be, so let's go bat mesh enable. All right. And then this is going to be bat mesh. Okay. And then these values, 1K is fine for that. 4.7 is probably going to be fine for that. But we need a 10K. This one needs to be 10K. 1K is going to be okay there. 10K, 10K. Okay, so those are okie dokie. Okay. Don't forget to save. Good idea. Let's do that right now. Save. Dropbox is dropping. Perfect. Lean Gamer, what have I stumbled into? We are designing a circuit board for with some sensors on it to do some sensor logging. Yeah, does KiCad have an autosave? I don't know. Hey Colin, either congrats or I'm sorry on also being a bald engineer. Never know if it's a good thing or a bad thing. I think it's a good thing. Since the bus has multiple circuits, are you going to use bus power rail? Dr. J, I'm not entirely sure I know what you mean unless you're talking about when I get over the circuit board. And in fact, I'm thinking about doing this as a 4-layer board so that we get really clean power since we're dealing with sensors. I think you use AREF on Arduino Uno. Not sure what you mean, Notion. Oh, did RJ? I missed it. Oh, so KiCad does autosave every 10 minutes. Cool. I assumed there was like a, there was something, I just, knock on wood, I rarely have an issue. So I haven't really run into a case where I had to recover a project. Or maybe I haven't, because it worked, I didn't even realize it. Okay, so I really wanted to get to a PCB layout. Oh, you know what we still need to do? Oh, man. I have PNP transistors in my inventory. I don't think I have NPN. Well, thing is, I don't have any clue where my transistors are. So, I don't know where most of my stuff is, but even if, The rest of my components, I have an idea of which box they're in. So what we're gonna need is an SMT NPN, and I care very little about which one we get. So something on the order of 10 cents is sounding really good to me. So let's go see what 45 volt, 100 milliamps. I mean, that sounds good. Does anybody have, in chat, does anybody have a favorite surface mount NPN and PNP transistor that they like to use? All we're doing is sensing voltages, so we don't need a lot of current. So VCE is not what? What am I thinking of? Oh, that was gain. That's why. Let's go for, what's its saturation voltage? VCE set, worst case 400 millivolts. Okay, but that's when the collector current's like at 10 milliamps. Yeah, okay, we're not getting anywhere near that. Okay, yeah, so this one looks like it will work, and it looks like it's in stock in multiple places. So, okay, we're gonna add that to our BOM. I'm gonna call this one, oh, okay, now that we picked one, we need to make sure our pinout's gonna work. So what's its pinout? Let's see, there are surface mounts 3904 and 3906s, 2222s. Okay, tell you guys what, I've got this one picked out, but just to humor you, I want to be nice, so let's look for a 3904. Oh, come on, it's twice the price. It's like 20 cents. Check this out. The other one is only 10 cents, but okay, how much current can these handle? 200 milliamps? Man, ooh, you guys are killing me on my budget. I don't know if I can afford that. Oh, God, man, 30 cents? This is ridiculous. You can get a really good capacitor for that much. Does this let me do a quantity filter? Because I want to, because these prices are kind of messing with me, because like a tape and reel, yeah, okay, it's only 18 cents, but do I have to buy an entire reel? Oh, minimum order quantity 1. Okay. You're paying for provenance and reputation. Oh my God. Oh God. Oh, also, okay. I'm okay. I'll back off. These are automotive. Are these automotive grade? I mean, automotive grade might be worth the extra dime. But I'm just saying. Yeah, the one that's actually 0.06 isn't, because I'm going to get it comes from Rochester, so I'm going to guess you have to buy a really high minimum order quantity. So I doubt this one is actually 0.06. I mean, for small quantity. Okay. I don't actually want that one. How about this? Rome. Is it at my favorite distributor? No, it's not. Okay. How about this one? 30 cents. You're killing me. You're killing me. Okay. This will work though, because we're going to get 10. I mean, God. So for those that don't know me well, oh, what do we got down here? This one from Onsemi is only 2 pennies. That can't be right. Is this on sale? I shouldn't have done that. That cost them money. Everyone knows automotive grade is overpriced. I agree, it is. You're not going to build a million of these? Probably not. Just buy 10,000. Yeah. Okay. This is, okay, so by the way, I mentioned this, I think, once when I was talking about buying passive components. Sometimes Newark, they just have fire sales on stuff. So like, okay, here these things are a penny. So, I mean, how can I not buy less than 100, right? I mean, that would be crazy. So what we're gonna do, we'll go MT, we'll take this part number. Oh, okay, wait, the next thing I need to double check is, let's look at its pinout. So it goes base emitter collector, and I think our symbol is wrong, right? Yep, our symbol's wrong. So let's get the correct symbol. So it's base emitter collector. So we'll replace that. And then the next thing we'll change in here is I'm going to add a manufacturer part number and a supplier part number. And then supplier for this one's going to be Newark. And at the end of the day, I may even end up ordering it from somewhere else where I don't get the special price. And we've already spent more time on trying to find this than I should have. But at least now we've got that. And then to double check, it is an SOT 23. So let's go ahead and go into footprint. We'll go to transistor. Let's see, SOT, surface mount, SOT 23-5, is it? Or wait, what is TO? Oh, TO 263. That's not it. Okay. Okay. Yeah, why is that saying it's a 263 when clearly it's not? Oh, 236. Hi, James, you should learn how to read. Okay, I don't know what that really means. So we're just gonna go for TO23, TO23, what, oh God, why don't I just move this over? Silly. Oh, you guys can't even see it, can you? Okay, so SOT 23, done. Okay, that makes it easier. Imagine being the guy that goes find the one item that is less than 2 cents, bags it, labels it, ships it for more than it's actually worth. So like literally true story, when I worked at the capacitor company, we did have one product number or part number of ceramic caps that it cost us more to put them in the reel. The reel, the plastic reel and the tape cost more than the actual capacitors. But there was just no other way to ship them, so we had to do it that way. Okay, so that's going to be our 3904. So now let's go look for our 3906. And so this looks like the Onsemi that we were just looking at. Doesn't look like Newark has the same deal. Let's go to new window. Yeah, these are a little more expensive, but I mean, at 5 cents each, we're not gonna get too upset. Okay, so let's go ahead and go with this one. And, oh, same thing. So let's go look at its data sheet. There's a 23-6, maybe that's what they mean by 236. Yeah, but I think the 23-6 is actually a 6-pin package. and it's definitely not a 6-pin package. So a long time ago, I looked into what all of the SOT packages were, and it made me wish I had never bothered. Okay, so this one is in a different package style, and I am going to be okay with that because then I have a visual, when I go to build these, they'll visually look different. So I'm not going to try to match the package. So we're good there. So in this case, now we have base emitter collector again. And so that should be base emitter collector. So this is not the right symbol either. So now we look for a PNP. Base emitter collector, right? So base emitter collector, all right. Rotate that around. And then use Y to flip that. Okay, so let's make sure. The collector is pin 3, emitter is pin 2, base is 1. Awesome. And then this is an SC70, which I don't recognize, and that's okay. So let's go find that footprint. SC70-8, that's not right. It has another number too. Let's try to be a little smarter this time. So SOT323, okay, I recognize that. Oh, here it is, perfect. And then we'll go with SOT323 SC70, beautiful. Beautiful. Okay. And then for names or the value, we're not going to put a value. So let's go MFN, supplier number, and supplier. Although I'm not going to, well, we found it, so let's just put this in there. So MFN, supplier number. Whoa. Whoa. Oh, no. Can you bring back the datasheet PNP versus NPN? What? Did I already close the datasheet? I think I did. So, oh, I see. Oh, I totally missed that. That this is a different, this is for PNPs and NPNs. So do they have a different pinout for both? No, just the one. So they must do the same pinout on both of them. So can KiCad generate parts list for purchasing? Sorta. The BOM management in KiCad, frankly, it sucks. I've used a couple of tools that help, but they're pretty terrible. Yeah, Michael, I totally get where you're going from. So yeah, so I didn't catch this earlier. So they're using the same datasheet for the NPN and PNP, and then I think what they're just trying to say is this is the pinout. I think that they just didn't show the PNP symbol, so we're going to go with it. But I am going to stick to having different packages for the NPN and PNPs because I think that's going to make it easier for me because they're going to be a slightly different size. So maybe it won't matter, but we'll go with it. Let's come back into here, supplier part number, and then we'll say Newark. And the package is the SC70. Yeah, so one thing about like the exports, for active components, if you can provide a manufacturer's, a manufacturer's part number, then most tools can take the CSV file that KiCad exports and do something with it. For passive components, that's where it really doesn't do a very good job because for a passive, if you don't have a manufacturer part number picked out, you need to have things like the value and the package. clearly spelled out. So a resistor is pretty easy because you generally can just say 10K 0805, and then if that description, you have that description string, they can usually match that. Capacitors, if you really want to use automated tools, then for like a capacitor, we would have to actually have a description that looks like this. It would say cap, ceramic, 10 microfarad, 0805, 6.3 volt, 10% X7R. If we do this, then a distributor site, the BOM tools that most distributors use, will have a very easy time matching to a good capacitor. Thing is, I don't care because for most of these passives, I'm picking what I already have in my inventory, so that's not a big deal. But this is one area where KiCad really falls flat, is it doesn't really manage this kind of detail very well. What I would like to have is like a library of the parts that I have in my stock, and then I would like it to generate descriptions like this for the parts that I have, so that if I need to order new parts or reorder or something like that, then I can get better descriptions from a distributor. So, fun fact, check this out. So when I worked at Kemet, I worked with the team that did our search engine. And so just to give you an idea, for when I'm looking for caps, I almost always come to this thing because it works really well. So like if I said 10 microfarad, 6.3 volt 0805, it'll know that I probably want a ceramic because I did 0805, and then it does a pretty good job finding. The other one we could say is, well, what if I want a C0G 100 picofarad capacitor? So now it's got a few more options. Let's do 1206, and then this should let it know that I only want surface mount. But what I want it to, let's do a voltage. Let's do 100 volt. 100 picofarad, 100 volt, that should be, oh, come on, didn't get close enough. Okay, what I wanted to show you was, so this engine is, the reason I like it is because they've actually taken some of the things that people might say for a capacitor, and so they might actually call it 100 puff. And so if we do this, this should still match the same three families. Yeah, because it's figured out that the, it didn't match it. Yeah, it should have, or unless that's what this one is. Let's take, yeah, I don't think it matched it. Okay, yeah, it should have matched 100 puff to be 100 picofarads. Anyway, oh, so many rat holes tonight. Okay, backing up. Where were we? So we got the two transistors are picked, so we're good there. Like I said, the resistors I'm not worried about because we're going to, I've got all those in my stock. Let's go for, okay. I actually think that gets us where we need to be, right? Or, the last thing, gosh, I can't believe we're still on the schematic. So I want to think about this. I really like this idea of using a regulator to enable the 3.3 volts. And then that way the microcontroller can actually turn the sensors on and off. Because that was something I was like kind of thinking about, how could we do that? You know, if the microcontroller goes to sleep, do we want the sensors to stay on or not? So here's what we're going, we're going to cheat a little bit because I have a regulator in mind, although I'm probably going to have to order more of these. But I have a regulator that I've already worked with, and if we can get them, then we're just going to get them. Yeah, see, this is what I was talking about. I had actually went through these packages at one point. So what I want is, so like I think the mic is the one that I used. So let's see if what the availability on this one is. It looks pretty good, and it's only like 10 cents. So we are definitely going to add this. Oh, you know what I didn't do? I didn't add the other one to the bomb before. So we end up with this 3906. Let's add that to here. Let me see, did we get, we don't have the 3904 on here. Shucks. Okay, so that's not the one I used. Now I gotta remember which one we picked. Was it this one? It was this one because these are all here. Okay, so let's add that to this bomb. So since we brought up, can KiCad generate the list of parts we're going to order? No, it can't. So that's why I'm using Octopart to generate the bomb as I go. And so this way, again, it's not going to have the passive components, but at least I have all of the sensors, and now I'm adding these active components. And then that way I have something there. This also gives me a chance to look and see, okay, I mean, right now, before PCB, we're at about 12, so let's call it $13. So these are gonna be about, in small quantity, about 15 bucks to make. If we go and do like a batch of 1,000, then they start to get more reasonable. You know, I think I could actually build and sell this for $15 and still make an okay money, or okay profit off of it. But I'm not sure if we're going to. I mean, yeah, even at 100, that's not bad. But that would require a pick and place machine, and that's going to be a different stream. Maybe I can send him to Unexpected Maker and have him pick and place them for me. Okay. So why is this coming up as two different things? Well, we're going to go with this one because my favorite distributor has it. DigiKey's got a bunch of them, so yeah. And I hope that's the one we added to the bomb. And if not, we are right now. So now what we're going to do is let's go to, so this one was the SOT 23-5. I very much remember that. Oh my God. Okay, so I think I have this part already. Here it is. Yes. And it's got the package. Yep. This is definitely the one I used before. Cool. So what we're going to do then is take VBAT. That's going to go in. And what's going to come out is 3.3 volts. And we're going to do ground. And then we're going to yet another pin. Oh my God, I can't believe we actually end up using kind of all of the pins on here. Enable reg. Okay. Remember something about undercurrent protection? Not too worried about that, I don't think. Okay, so what we got to do now is I need to understand how this enable pin works, because this is what I screwed up the first time I used this part. So I need to go back to, I'm just gonna go back to the thing I wrote. So, so after reviewing, so didn't I say on the one that I used? Maybe not. Okay. Long story short, the reason I pulled up this article was that I had 3 different LDOs that I had planned to use for the design that I used this MIC 5504. And I found out that the enable pins did not work the same across every single part. And so, for example, some of them are called shutdown and some are called enable. And at first I thought that was just a naming convention, or just, people just use different words. Well, it actually turns out that a shutdown typically means that there is a resistor. There's a resistor that gets connected through a transistor. So when you shut it down, it actually allows the output capacitor to get discharged. It also turned out that some regulators on their enable have that same capability. And so it was just kind of surprising me because I always thought the enable pin just, turned it on or off, but there was a little bit of subtlety to how they work. So what we're going to do in here is we're going to look for enable. So let's see, enable goes high and then it takes a little bit to turn on, something we can measure on the scope. Enable turn on. So it is enable input is active high. When it is high, it's on. When it is low, it is off. For MIC 1 and 2 do not leave floating. 3 and 4 have an internal pull down, which means, and somehow I misread this first time, has an internal pull down. So if it's pulled down, it means it is off by default, which is cool. That means we don't need an external resistor. And all we need to do is give it a voltage and it turns on. Now, the reason I'm saying that is because this was in the Pyramid Arduino debug and turn on video. I actually, when I read this the first time, and I totally remember this now, I read MIC 5504 has an internal pull down. And I didn't even think, I said, oh, cool, that means it's enabled by default, which it doesn't say this, but no, it means it is disabled by default, which is cool. That's exactly what we want. So then we're going to do this. And what did I name this? Enable regulator or reg enable. This should actually be reg enable. Okay. Oh, and then I think we need, what did I just do? Then we need a couple of decoupling caps. And, oh gosh, did I already close the data sheet? Nope, that's the wrong one. Because I think this tells us what the input capacitor of 1 microfarad is required. Okay. This really bugs me. Wi-Fi, I take that back. They wrote this correctly. So X5R or X7R are recommended. Wi-Fi V or Z5U are what I call shitty dielectrics because if you breathe on them, they actually lose most of their capacitance. And then the output capacitor of 1 or higher will maintain stability. It's been optimized for 1 microfarad. Yeah, so what we're gonna do is we're just gonna put 1 microfarads on both the input and output and call it a day. Copy these grounds, delete this, and then let's do a wire up to here and move this one down. Now, one thing that I'm thinking about is because of the size of this board, we probably don't need to populate every single sensor with a 1 microfarad cap. So what I'll probably end up doing is I'll probably put a 1 nanofarad just because small board, we don't have anything having really high current. And if we have a 1 microfarad already from the output of the regulator, we're probably going to be fine. Also, it'd be kind of a fun project is we could actually populate one of the boards with 1 microfarads, another board with all 100 nanofarads, and maybe a third board with no decoupling caps, and then see what the power rails do. That would be fun. Maybe label it enable 3.3 volt. Let's do this. Reg 3 volt 3 reg enable. I like that suggestion. So we will do that. Second mouse button to move that over, delete this, and then move this one up to here. Can you share the link you were looking at in chat? Oh, sure. This is the article. And this is the, if you're just curious, that's going to be the regulator that we're going to use. What voltage is VBAT? It's going to be a lithium ion, so it's going to be between 4.2, ooh, good question, or good point, 4.2 and 3.7. So what is our dropout? Dropout at 300, yeah, well, the problem is we're not going to be dropping 300 milliamps. So we need the graph that shows us what the dropout voltage is. Because good point. I totally forgot. In my previous usage, I was at 5 volts. So dropout voltage in millivolts when the output current. Okay, so if output current is less than 50 milliamps, our dropout voltage is 20 millivolts. Wait, what? Isn't this backwards? Isn't it usually as the current goes down, doesn't dropout voltage get tighter? Am I reading this graph right? So this is telling me that, let's say 50 milliamps, which is nowhere near what we're going to, I mean, that's way higher than this thing's going to draw, that I can go down to 3 point, that it'll work at 3.32 volts and it'll still output 3.3? Huh. I feel like I'm reading that wrong. Because what at 300 milliamps, it's a 160 millivolt drop, right? So that means if I want 3.3 volt out, I need to have at least 3.46 volts in. So this is saying I need at least 3.32 volts in to get 3.3 volts out at really low current. Huh. I don't know why I don't believe that. Okay, good. And with temperature, okay. All right. This regulator just got me even more excited. I mean, as much as a regulator can. Yeah, okay. Cool. It is called low dropout. Michael says it is called low dropout for a reason. Yeah, that's a really, really good point. Okay, so that didn't take long to add that. So let's put a title over here, and then let's say onboard 3.3 volt regulator. Okay, let's save this, zoom out. So VBAT will come into here, and then we'll use the pin to enable it, which is going to be so cool. We are going to put, I do want to do this. I want to add a pull-up resistor in the event I don't want to control this. Let's just add a pad to, oh, I don't know what just happened. In the event that I don't want to control it, let's add a pull-up resistor so that we can just solder on a pull-up, and then this will get enabled by default. So we'll do something like that. Yeah. Yeah, this chart does look a little too linear to be true. Yeah, I mean, that's why I'm looking at it just thinking, because I mean, even at 0, I would have thought it would be just slightly above, but we'll see. We will see. Okay. So what we will do is I am still going to leave this header. And in fact, we'll move these. How do I want to do this? Because I'd like all this stuff that's related to be together. So maybe we'll move this down here. Because what we are going to leave, oh, we need to change those names. Okay. We're going to leave the header pin or the header jumper for the 3.3 volt. Oh, you know what we could do though? I changed my mind. We're going to delete the header pins because we don't need that anymore. But now I can't measure the current. Because one thing I do want to leave, okay, I think we are going to add header pins. So I'm going to leave this jumper in. That way we can, if we need to ditch our regulator, it's going to be easy to get power from the featherboard. So we'll leave that. I like that one. What I was going to say is let's invisible that and invisible that. Okay. Now, let's move these like over here. USB. Actually don't need that anymore. Okay. Move this, delete that note. Let's just move this up to here. Okay, got that. And then what I'm thinking about is we're gonna move this over to here. This is kind of, don't really have a good home for pull-up resistors. Maybe I'll just to group something with them. We'll put the pull-up resistors and the LED together. All right. And then, okay, pads for pull-up. And some debouncing caps to the jumper. So this is likely to be a, oh, it's not going to fit perfectly, is it? Okay. Don't really care about that value. Okay, so now we can delete that. Just gonna leave those. So what I was thinking here is we could still do another jumper. And instead, what we could do is delete this. And then this way, this is kind of messy, but at least you guys will see what I'm thinking about. So what I can do is this way I can put header pins in, and then I can measure the current from the regulator to the 3.3 volt bus. And if I don't want to do that, then I can just solder this jumper together and we'll be good to go. Hey, Godick, thank you for the follow. Are you saying add some caps to the jumpers? I mean, the jumpers are, they're just going to be header pins. They're not like buttons. Okay. Oh, yeah, I think I understand what you're suggesting, Dr. J, but I'm not worried about it because I'm only going to have like these populated a certain time. And I can't really add caps to any of these signals because that'll mess up the signals. So, okay. So, so let's see now. 3.3 volts from the feather comes in here, and then there's going to be a jumper so that we can enable that directly. And then, oh, I see what you're saying. You're saying add bouncing caps to these jumpers, maybe. Yeah, the thing that I'm worried about is I think we're already going to run out of room. So I want to, let's see if we have room for even more caps. So, okay, so this, and then this, okay, so this jumper exists so that we can bypass our regulator. And then on the regulator, our signal comes in and it's defaulted to getting pulled up by battery. But this is going to be a do not populate. So, oops. So this will be a do not populate. So I probably won't even, in fact, for its value, let's do DMP because, oh, well, it'll show up. Well, we'll do this. Because the only reason that I want that there is in case I decide that the enable signal is not helping us. So then on the output, we will go either to a header pin so that I can measure the current, or more likely we'll just do the solder jumper. And then what I actually wonder on this one is it may be better to make this a default connection because it's more likely that I'll want to use this than the other one. So jumper. So I want this instead. Because then that way I can just cut it. And most of the time I'm going to want this to be here. These header pins are only there for one measurement. Fusing AAA batteries with 800 milliamp, the LDO alone will draw 40 microamp, which will last 20,000 hours. Awesome. Thanks for doing the math. So Tax Z, the problem with that calculation is, and this is what a different article I wrote touches on. So let me see if I can find it, because the problem is you have to think about the leakage of the ceramic capacitors, which is what I was talking about earlier. What is Nope, it's not that one. Man, some of these are old. Where is it at? Where is it at? What did I call it? Man. Voltage regulator, let's try. It was definitely after that one. But no, okay. Let's just see if leakage works. Yeah, nope. 5 voltage, GSM. Gosh darn it. Don't you hate this? Man, when was it? It was like, I don't know, 2 years ago. Anyway, long story short, the leakage on a ceramic capacitor is actually worse than the LDO. And so while the LDO only draws 60 microamps, the input capacitor on the LDO could be drawing like ooh, getting close. I can picture I know what the image looks like. Why can't I find it? Oh my God, it's driving me crazy. So I'm gonna be so mad when like the title is ceramic capacitor has lots of leakage. It might actually be in this one now I think about it. So the picture is like just my DMM, my bench DMM. So why can't I find it? Where are you at? 20 Mushi meter. It was definitely after I reviewed the Mushi meter. So then why do I not see it? Did I delete it? Oh man, that'd suck if I deleted it. This feels like I'm getting, because it was part of the Raspberry Pi project. Oh my God. I thought this was a separate post. Oh, it wasn't. It was in this post this whole time. What components can go bad with time even if you don't use them? Electrolytics, they have a wet electrolyte that dries out over time. And ceramics actually have an aging where they lose capacitance over time. However, it's not destructive. You can basically, if you reheat them to their Curie point, the aging resets. Also, it takes like a decade before its capacitance drops more than a few percent. Anyway, what I was trying to point out was I designed a different LDO circuit, and it was supposed to only have like 40 microamps, but when it was when it was disabled, I was actually measuring 370 microamps. And what I figured out was it was the, nanoamps, not microamps. Okay, because it's 0.3 microamps. Okay, God, so many rabbit holes. Okay. Yeah, anyway, you just have to be careful. Like if you get into like 100 microfarad ceramic cap, it could have a couple of microamps of leakage. And so just something to be aware of. Anyway, good gosh. Okay, so where were we? So then power's gonna come through here. I'm gonna use this jumper and cut it on the boards where I wanna measure the current, and then we'll have the jumper there for that. Okay, we'll have a solder jumper for the power LED because it's more likely I don't wanna use that all the time. So we'll do it that way. For the battery enable, for the battery measurement circuit, so the PNP, we will use, this will be connected to the microcontroller so that there's no way for the VBAT to get back powered because it's not going to jump from collector to base. And then we'll use this to turn the voltage on and off on so the NPN will control the PNP, and then that will allow us to do a voltage divider to measure the battery. And again, this is so that we don't get any back powering. Okay, that looks good. So VUSB up here, this is this is really just because we have an extra pin. So I figured, hey, why don't we see if we're connected to power or not? Because what I'm sort of thinking here is, let's say we're in a situation where the sensor board detects that we're plugged into a computer. There's no reason for the microcontroller to go to sleep. So we'll do that. I don't know if there's not really a software way to tell. I don't think most boards have a software way to tell when they're connected to USB. So that'd be pretty easy for that one. Okay, that's our override. Okay, so on the microphone, we have our clock out, clock data, PDM clock, PDM data, PDM clock, PDM data, APDS int. Over here is APDS, SDA, SDA, SCL, SCL. Okay. And over here, so SCL, SCL, SDA, SDA. DS3231, 3231, okay. So the real-time clock has 3231 reset, 3231 interrupt, 32 kilohertz. Didn't name that one DS3231, but I knew that wasn't going to show up anywhere else. SDA, SDA, SCL, SCL. Alert signal, same thing. Not really sure if we're going to use it, so why not put a solder pad on that one as well? And the reason I did that is because the datasheet actually said if you're not using it, leave it floating. So, which I guess if you go into a high impedance input, that is effectively leaving it floating, but okay, SD, D out, D in, I want to make sure that is definitely a capital I. Chip detect, okay. Pull up resistors for SDA, SCL. Cool, I think we're in good shape. And so bat mesh, VSB mesh, VSB mesh, bat mesh enable, bat mesh enable. Oh boy. Oh boy. Hey, init us or init us. So we're making, I'm calling it a sensor wing. So there's the Adafruit series of feather boards, which are different microcontrollers with a bunch of different capabilities. This is a board that will include a temperature, humidity, light, and sound sensor. Well, there's three separate sensors to do that. And then there's also a real-time clock so that we can do data logging to a micro SD card. So that's what we're making. It's called a wing because Arduino has shields, and so the feather boards have wings. Okay, I guess because they're light as a feather so they can fly. Okay, let's save that. I'm going to take a quick break, and then when I come back, we will start the process. We'll run CVPSB to see if we missed any packages, and then we'll head over to the PCB. And at least what I want to get done tonight is just kind of lay out some of the parts and find out, is everything going to fit onto the board? So yeah, this schematic is getting very complex. It started out pretty easy. I am glad, seriously, the nerd in me is like, I'm really glad we did this battery detection thing, or battery measurement circuit, and the onboard regulator, because the rest of these, we basically just copied Adafruit schematics. So, which, I'm very, love everything they do. I like to support them. But I just kind of was like, man, all we're doing is is copy and paste. But at least we did a little bit of design, so that's cool. Any idea on the board size? Yeah, actually, we already know what the board size is because it's a defined form factor that we're going to be trying to fit into. So just to give you an idea, so I think this is, let's go from here. Let me do it from here to here. It is a 50 millimeters wide, and what? I did that wrong. Yeah, so, okay. Yeah, so it's about 50 millimeters wide, and it is about 23 millimeters tall. So 50 by 23-ish. So yeah, so we're gonna try to fit everything onto here when I come back. Okay, so I'm gonna take a break. hit the restroom, grab some more tea, and I will let you guys play with trivia for a couple of minutes. I don't think I'll be much more than like 5 minutes. So is it like an Arduino shield? Yeah, basically this is a shield that plugs onto one of these feather boards. Before I go, just so that we're clear, what I'm talking about is Adafruit 10 feather. The feather boards look something like this, or here we go, good image. So there are a bunch of different, and then there's a bunch of different microcontrollers. They have different types of radios. That's why I decided to go this path, where we'll just make a wing or a shield that plugs onto them, because then this way I can pick whatever microcontroller or RF interface I want, versus trying to cram all that stuff onto my own board. It'll also be a little bit cheaper, at least for me, because I already own some of these. So basically we're just doing just the shield or wing. So, okay. I'll be back in just a couple minutes. Let me know if you think of anything while I'm gone, and I'll double check the chat when I come back. But for now, I'm gonna send you guys over to trivia, and then like I said, I'll be back, give me like 5 minutes. That did not work. Okay, I'm not pressing that button again. All right. Sorry, I was finishing a snack. Okay. So I wanted to roll back on, right before I left, there was a couple of questions I wanted to address. And TaxZ was asking, when battery powered or normal powered, who decides where to draw power from? So the way that feather boards are typically implemented, they have a lithium ion charge controller that takes either 5 volts or power from the battery, or the 4 volts from the battery, and then it outputs the Oh, that's a problem. Okay, because then it outputs the 3.3 volts. What I'm realizing, we got to go look at that, because what I'm realizing then is, even when we're plugged in, oh yeah, no, because even when we're plugged in by just USB, then our sensor board will not get any voltage because they're not, yeah, okay. So let me double check that. And then Barry was asking, open collector bus. Not sure what that reference was. I mean, I2C is an open collector bus, but did you build a light for your mic yet? Nope. Still trying to be, still just trying to get better about it. That is a project we're going to do though, because I really want to have like a VU meter right above my monitor. And when I'm down in the streaming from the lab, I'm going to have a completely different streaming setup. So I want to be able to glance up at the screen and see the VU indications. Anyway, so let's go to the schematic, because let's see. Hey, Dalian EXE. So the way that Adafruit does this on most of their feathers is they get V-bus comes in to this LiPo charger, V-bat comes in to the LiPo charger, and then, okay, so this does work. Okay, that's how this works. So V-bus comes in or V-bat comes in, and then the idea is V-bus will actually provide enough current to V-bat to hold V-bat at, say, 4.2 volts to charge the battery. And then that, okay. So the long-winded answer to the question of who decides, the feather board will decide, because what it actually looks like it does is there's the 3.3 volt regulator, there's a diode on the battery, so there's just enough to cause a difference, so that if USB is connected, then there's not going to be any, this isn't going to conduct, so the battery is disconnected from the regulator. So, long story short, the feather will decide which source provides voltage to 3.3 volts. The problem is that V-bat isn't always powered, except that it is, because it gets powered through the LiPo charger. So even when we plug this in, I think this will still power up if it doesn't detect battery. Worst case, all it means is that even when we're connected to USB, we have to have a battery connected. So, yeah. Okay. Michael suggests that we actually just change our jumper so that we can decide where we get power from. That is a really good idea. We're going to do that. How are all the power lines going to be connected? I'm actually going to do this as a 4-layer board and have the inner layers be 3.3 volts and ground. And then the outer layers are also going to be ground, so that we get a really good shield. Yeah, that's what we're going to do. if you stack boards, you'll need to make sure that they all have a way to communicate. Yeah, I mean, I agree with that. However, I'm not expecting this to really get stacked with anything. For one reason is because we've sort of used up all the pins. So it'd be hard to stack. But yeah, I briefly considered how we would handle that, and my decision was we're not going to. Okay, let's do this. So I like this jumper idea. So the idea is we have 3 volts from the feather. Wait. Okay, we're good. Okay, I'm actually not going to do, okay, I just realized this. So maybe I will end up populating these through holes on all of the boards, because we could always just run a wire from here to here and get power. So yeah, you can open collector bus. Yeah, we're sorry, I'm not adding that much complexity to the board. I mean, it's, yeah, I don't see the value of doing that. For its intended application, the only thing I could see getting stacked on would be a I2C display. So, okay, so so Michael, I liked the suggestion on the 3-way, but I think we're just going to leave it this way. Yeah, and software may have to do a lot of multiplexing. I mean, don't really think so. Okay, let's go ahead and see if we can get some okay, first we have to annotate. Let's see what is missing footprints. Oh, why is this so slow? I don't understand. Yeah, I wouldn't say multiplexing we have to do a lot of, but we are going to have to do a lot of juggling, because we'll be, because I mean, there's going to be a lot going on with the sensors, but you know, what I'm thinking in terms of software structure is similar to what we did with the Grove board a couple weeks ago. So we'll wake up, and then we will turn on all the sensors. Maybe give like, I don't know, 100 milliseconds or so for everything to get powered up and stable. We'll check with the RTC to see what time it is, so we'll get the timestamp, and then we'll just go around to each sensor and ask for its current state, and then we'll write that value as a string out to the SD card and go back to sleep. If the feather that we're using has a radio, then we'll also decide how often do we want to transmit. And so, you know, like if it's Wi-Fi, what we might do is maybe every 10 or 15 times we wake up, then we transmit the last 15 readings. On the other hand, if or we may just transmit it every single time. I don't know yet. That part I'm not sure. We'll have to we'll play around and see. That part is why I wanted to have the header pins on the 3.3 volt line, so that I can hook up a current meter and we can accurately measure how much current is the thing drawing when it's awake or asleep, because then we can figure out how long we can stay awake and how long the battery will last. Hey, PRC Planet, good to see you. How are you doing in Taiwan today? Yeah, it should be like, what is it? It's probably first thing in the morning for you, isn't it? Some of the assigned footprints have legacy, libnames would convert them. Okay, I'm going to say yes, and then I'm probably going to wish I had it. Yep, I wish I had it. So that wasn't found. That wasn't found. Okay. All of the ones that we created were not found, I guess. So let's save that. So we have, these guys are all good for the power LED. I really hope we have space for this because I have a bunch of 1206 LEDs. So we're just gonna put a 1206 pattern. Solder jumper. Oh, why didn't that, oh man, I feel like we did this before. Where are the solder jumpers at? Nope. Nope. I've seen the MP34 is deprecated because it's not going to be produced any longer. Yeah, I noticed that too when we picked it, but because I've never dealt, because that's the microphone, right? Yeah, because I've never dealt with a PDM microphone, I'm getting that one simply because Adafruit uses it in their design. And I want to be able to use their code because it's totally new to me. So my thought was, at least on this first batch, let's get that one. That way we can get it up and running, and then we can go and look and see what other microphone we can find. So yeah, but I am aware that it's not suggested for new design. I mean, at this point, I'm not, well, I'll put it this way. When I first started doing this, I wasn't planning to make this a product. However, a friend of mine has been trying to talk me into making it a product. And so if I decide to make more than say 10 of them, then yeah, we'll find a different microphone. But we'll probably also change the real-time clock as well. Part of why I'm using the 3231 is because it's very accurate. I like it, and I've already got a bunch. Okay, I don't remember where the solder jumpers are. That's driving me crazy. Oh, there is one called jumper. Okay, so this is for the solder jumper open. So bridge, 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 pad, pad, triangle. I don't know what these look like. Okay, so what did I just do? How do I, doesn't this one like at least have, why doesn't that other tool have the, because this is what I want to see. So this is for the one that is, this is going to be open. So let's look for a good pad for that. So do I want this one or this fancy triangle? Ooh, that's pretty. We're gonna go with this one because this is what I've used before. Or is there a bigger one? These are all 3-pin. Okay, so we'll do this. And then I'm gonna copy that because we're gonna need it again for this one. So edit here and just paste that footprint. And then it's not valid. I think it is valid, but okay. Whatever you say, cowboy. Let's edit this one. Okay. And then this one up here, this one needs to be bridged, which should be, this is like this one. Okay, cool. Let's see, my concern is milliamp surge of waking all the sensors up at once. I'm not overly concerned about that. None of these are super high power. And, okay, that is a valid concern, Dr. J. So let's see what happens. I mean, we'll get this one back and see what happens. The alternative is we do some kind of sequencing where we turn them on, but I'm not ready to spend time designing that because I don't know if it's going to be necessary. But I see where you're coming from, is what's going to happen, you know, how much current are how much stress are we going to put on the battery whenever we turn the sensors on? Babin is asking, what is a solder bridge? Okay, so for example, here I'm connecting the V out of the regulator to the 3.3 volt voltage rail. And so the solder bridge allows me to connect between these 2 points. But what I can do is, like, for example, this one, there is a short. But if I want to disable this connection, then I can take an X-Acto knife and cut the trace so that I break this connection. On this solder jumper, the traces are naturally open. So I can just take a piece of wire or my soldering iron and blob a piece of solder across the 2 pads to create a short circuit. So it's the same thing as jumper pins, but we either break or open them using solder. The reason I like these is because they're much smaller than solder pins, and they're kind of meant for things that aren't going to change all that often. Couldn't the surge be eliminated with a single cap? So the problem with the cap is you have to charge the cap up at some point. And then if you have a relatively big cap charged, it's going to be drawing current even when everything's off because it's going to have some amount of leakage current. So, but the primary problem is then what you want to do is you want to charge up the cap before you turn everything on. And that just, again, starts to complicate things. But I foresee us actually doing some cool measurements when I get this back as part of a stream where we actually measure and see what happens when we turn, how we turn the board on. I'm going to borrow some things from work that will make that happen. Also, I have one of those jewel scopes that was on Kickstarter, and so I'll finally get to use that. That'll be fun. All right, connector 2.54, and we need a 1x2, and horizontal, vertical. Why are there's like 5 of these? Okay. Oh man, I just thought of something. Excuse me, I'm sorry. We should have done, we could have put test points because I got these really cool test points that Acetin told me about. Okay. So where's the parts that are missing that it's claiming that it doesn't? Okay, let's save. PCB, tools, update PCB. Cannot remove, locked. Cannot add, not found. Okay, so it's still not finding those 4. Okay. So we'll go back in here, and it's these 4 that we created. So let's go look in the footprint. There should be one called My Libraries. And this one is, I'm looking for the Amphenol. Where'd it go? Uh-oh. Well, I understand why it can't find them now. Okay. I wonder why that happened. Okay. So what we're going to do is go into the footprint editor. A small cap. Well, now you're getting to the problem of if the cap is too small, then it doesn't help you, and if it's too big, then it becomes a problem. I think the right answer is we will find the correct way to measure what the surge is at the time of turn on, and then use that to determine what we want to do. I mean, one thing to keep in mind is I am planning to use a lithium-ion battery, and those things are really good at power delivery, and so I'm not too concerned about the stress on it. Now, if I was using, say, like a crappy 9-volt battery, then yeah, we'd be we would be losing a lot of energy during that turn on phase because the battery is super inefficient. So let's see, where did I put this? I thought I had this and download it. This one. So I imported that. Okay. The name of it is Amphenol blah blah blah. And this should be save changes to library. Amphenol la la la. And I want it to be saved into my libraries. Save. Okay. So why did that happen? All right. So now let's do import footprint. And then the next one we want was the APDS. Okay, awesome. Great. I was really hoping it wasn't going to work. That's fantastic. Let's try, what's another one? The MP34. Okay. So let's save MP34, and that's going to go into my libraries. Okay, that's really weird how it like goes back to the project manager every time I do that. Okay. Import footprint. So what's the SHT30? Okay, save that, and I want that to go into my library. Okay, so let's get those three taken care of, and then we'll come back and deal with this other one. So now, my libraries, DF la la la, okay, that one's good. Let's come into this one, change its footprint to Amphenol, okay, and then SHT, this one, the microphone. I think it's actually called mic. Yep. All right. Now, save that. Let's go to PCB and just make sure that it's happy with those. So these are okay, and then we got to figure this one out. Maybe after installing the new software version. Oh. No, it's actually even sillier than that. This is a different computer. We added them to my library on my laptop, and now I'm on my desktop. And so the library, I didn't realize this. Maybe the library isn't, I thought they were the same library was in a Dropbox folder, but maybe it's in a different place. So that's weird, because I thought I was, I'm not going to do this on the stream, but I'll go back to my laptop and see if the parts are still in its library, and then I'll upgrade and see what happens, because this should have worked. Or it could be, maybe I didn't add them to my library last time, and I just thought I only added them to the schematic library, but not the footprints, which is, I think that's what happened. I think I didn't actually add them last time. So what are we going to do about this microphone? It was the APDS. If we try to import that, expect it. Okay. So let's go take a quick look at it and see. If we can figure out what it's complaining about. Let's open this up with Sublime Text. Okay. And it's saying line 3 offset 79. So line 3, 79. Expecting, well, that doesn't line up to anything that I see. Description. Let's just take this out. I just wonder if the quotes are messing us up. Import footprint. Yeah. Okay, that was easy. We are designing a circuit board. So, yeah, so we're using KiCad to design a circuit board. There's a closed parentheses on end, but none on starting. Okay. Yeah, I think what was going on is I think the quotes in the HTML was causing trouble with the description. And so I think it got confused to where the description ended. And so I don't really care. All it did was point to the data sheet, which we already downloaded. Okay, so let's save this into my libraries. And now, oh, this is so cool. I like it when stuff starts to come together. Let's come into here. Change its footprint to the ADBS. Okay, save this, go to PCB, and then Tools, Update from PCB. I guess there is a button for that. And the only thing it's complaining is that the references are locked, which is okay. So we're gonna say okay. Oh, crap. Oh, man. That battery is huge. Oh, man. Oh, boy. Oh, boy. I'm going to import that again because I don't. Oh, gosh. Okay. I forgot about the battery. Oh, God. Oh, okay. So, we have our work cut out for us. This is for certain. Yeah. All right. Well. Okay. So let's just kind of. I mean, a couple of these are going to be pretty obvious. They're going to. This is going to go something like this. And then oh, dang it. I mean, we could put the battery on the back side, but then these are really tough to, I don't want to solder that. Oh, look at that. That is not, I mean, this thing takes up half the board. Okay, let's just how do you turn Rat's Nest off? I'm just, oh, this is gonna be, I've never done something this tight before. Oh man, I wish I hadn't said that out loud. Oh gosh. Oh gosh. Is it CR2032? No. It already is a 1216. Yeah, it's already a 12 millimeter battery. It's not a 20 millimeter. So this is the small one. Okay. Hey, okay. We might still be able to make this work. I don't know how. Let's see. So let's just kind of. Okay, so if this is going to happen, it's definitely going to be a 4-layer board. I can, no question about that now. So this is okay. So this is the come on. So this is going to be the real-time clock. Can we, let's do a rotate. Preferences, let's change our rotate to be 45 degrees. Where'd it go? Used to be in here, right? Field name, display. I thought it was in here. Okay, I guess not. Common, graphics fallback, canvas size, okay. Where do you set, why project managers have a hard time understanding why schematics take so long. Yeah, you're just writing down what's in your head. How hard is that? Yeah. Okay, it moved, or I don't remember where it's at, but I want to change the default rotation so that instead of being 90 degrees, it's 45. Nope. What's automatically place components? Hold on. Place, automatically place selected components. We should have tried that at first. Maybe we'll reload we'll reload at some point and see what it tries to do. Maybe grid settings. Nope. Oh, this is frustrating. Track and via? Nope. PCB new, preferences, general settings. Yeah, I think that is where it used to be. Because there's no, oh, what's in here? There it is. Thanks, Babin. I just did not go to the right thing. So, let's see, Zach Harden suggests the 123. Yeah, that's a good idea. We might have to go to one of those cells because that's, I think if 123 means like these smaller batteries that I'm aware of, the reason I did the 12 millimeter is because I've already got the clips and I've already got the battery, but maybe it's not going to be big enough, or maybe it's too big. So we'll have to figure that one out. Here's a thought. Why do we need a separate battery for the RTC? We have access to the battery we've got access to the other battery. So why don't we just use that? Okay. Let's do a quick check on the datasheet and find out what's the maximum battery voltage. The DS3231 RTC datasheet. This is from Maxim. Recommended operating supply voltage, VBAT, max of 5.5. Okay. I'm gonna leave it here for the moment, but it just occurred to me we don't need a coin cell battery because we have a battery. We'll just use the VBAT from the Feather. And the only downside of that is if you disconnect the battery, then we'll lose the clock. But we'll deal with that here. I mean, that might be a trade-off we just have to take. HL521. Yeah, I kind of feel your pain. I've been using my laptop for the last 2 weeks as I was moving. And now that I'm back on my desktop, it's really nice to have something that just works. Although my desktop in the move, one of the fans has stopped working. And I don't know if it was because of transporting it or if it was because I was folding at home for so long that I wonder if the fan got worn out. But yeah, one of my case fans stopped working. So we'll have to deal with that at some point. Okay, So let's get this roughly to here. And then where's the other sensors? Let's get this sensor to roughly here. And then let's do this one. So then we've got all these passives. This is going to be our voltage regulator, which we'll put somewhere up here. This is going to be to measure the battery voltage, so we'll put it around here. There should be another transistor somewhere. Here it is. I'm just going to put it there for the moment. Let's turn off the, is that courtyard? No. Drawings? No. What's the other gray? Fab. Yeah, let's turn that off. That's just noise at this point. So TACZ, so the CR1216 is not going to be driving the LDO. It is only to drive the real-time clock. And so it's only so that the real-time clock can keep time. So a couple things I'm realizing is, one thing is it's pretty ridiculous to have such a big battery for the RTC. I'm also realizing why the other coin cell holder is so popular, because it takes up a lot less space than this. So we may even just consider that as just change that. But yeah, it's not, this coin cell won't drive the LDO. It's only for the real-time clock. Although 660 hours would not be a terrible operating time if we had to go with that. Put a solar panel on, yeah. For the outside, I mean, for the ones that'll be going outside, that isn't a terrible option. So let's just move. Man, all of the little things that okay. Yeah, I mean, we're just not gonna, this isn't gonna make it. Right? I mean, let's be realistic. So step one would be, we could change this footprint. I'm really debating if we even need it. Because even if it loses the track, even if it loses track of time, whatever default time because like what I'm thinking about is if I move it from, say, the computer to where it's going to be, or I swap the battery out and it loses track of time, it's not the worst case, because it'll still keep track of time. It just won't know what time it is, right? And then that way, at least we get a accurate timestamp, versus like when we were doing it with the Grove board, where we were using millis. So, okay, step one, let's try a different footprint for this to see how much space that opens up. And then step two would be, if we can't make it work, then we're just gonna chuck it. So let's go back to the schematic and go to this guy and open up our viewer. So we want a 12 millimeter, so not quite that one. What I'm thinking about was the one that looked like, man, that's 23 double A's. That's not gonna do us any good. Yeah, we could get, I wonder what this, so 6.8 millimeter battery, that might be more reasonable. I guess there isn't one. Okay, I thought there was like a better, oh, these are vertical. Yeah, I don't want that. Okay. Yeah, so the only other thing I could do if I really wanted to keep a battery on here is go to this other damn. How would you figure out the time offset though to get to know that it is correct time? I mean, you could we could just. I mean, you could just kind of guess. Take the SD card out, see what the last timestamp is, and back it out from there. Does kind of make me want to have a push button so that you could force a sample or something. Okay, I think. Oh. Just thought of something. Okay, we have a battery available. Really big battery. Biggest battery there is. Beautiful battery. Tremendous battery. So we don't have to get this one to fit on the top. We can go ahead and just put this on the bottom, and basically we'll just throw it like right there, and we'll put it on the bottom side of the board. And even if we get to the stage where we decide to sell these, then it'll just be up to the user to solder this on themselves if they want to have a coin cell battery. Yeah, that's what we're gonna do. So in fact, I'm gonna just move that out of the way so that we're not even. I don't know if I just turn off bottom, would that disappear? No. Can you turn off bottom components? Okay, so guess not. Why are those disappearing when I turn off footprints back? That doesn't seem right. So oh, these must be polygons. They're not. They're probably not pads. That's why it's not. Let me shut them off. Okay. So this shield will plug onto an Adafruit feather board, and not all of the feathers that I plan to use these with will have radios. So network time is not always going to be an option. Now, when it is an option, we'll make use of it, which is also why I'm coming to the realization that, like I said, if this ever got to, I wanted to make a bunch of these, if this is the only thing that you have to hand solder on the back of the board, so that would be okay. I think that's an acceptable trade-off. So, oh, why every time? So diode, oh, that's our power LED, so that's probably gonna go up here somewhere. And then I should turn the rat's nest back on so we can see where these capacitors are at. What we can do is, let me go side by side with the schematic. Can I turn the manager off? I don't see how to turn off the library manager. There we go. Okay. So that is for the transistors, whereas C5. C5 is meant for the onboard regulator, so that's probably okay where it's at. R3 is for the SHT, so let's try to get that up to like somewhere around here. R12 is the pull-up for the I2C, so where's I2C? They're going to be over there. Yeah, that's not going to work, but let's just maybe we'll just leave them where they're at for now. So JP3 is for the, we may chuck that one because that's just not enough space. I still want to keep the jumper for the LED. And then this is jumper for the output of the regulator. R4 is input to the regulator, so that's going to be around here somewhere. C7 is for the SD card, so we'll just kind of put that somewhere around here. C4 is for the SHT, so this is overlapping, but that's okay. Kind of do one of these. Start with the external battery and then see if you can make something fit. Well, so the FeatherBoard has an onboard LiPo controller and jumper or header for LiPo batteries. So I'm already planning to use that anyway. And in the design we came up with, we're going to use the battery voltage to power the sensors. So I can just use that same to power the real-time clock. Well, we still have to go back and edit the schematic for that, but I just sort of want to wait on that for a moment. In fact, let me just add a note. To do jumper for VBAT or coin cell. So we'll come back and do that in a minute. For now, I just want to get a sense for what have we gotten ourselves into. And then in fact, I'm going to write a note up here so I don't forget to do coin cell VBAT jumper for RTC. And that way we'll just, like I said, I just don't want to lose sight of it. Okay, so this is also going to somehow get near this regulator, which is now basically out of space, but we can move all of this stuff. Let's move all this stuff. Like down here maybe? What? Okay, move this stuff over here. And then let's get this guy up here. May have to give up on that idea. What size are the resistors? All of the surface mounts are 805s, except for the LED, which I made 1206 because that's what I have. But all the other passes are 805. If necessary, we can go to 0603 because I can still solder 0603. The reason I didn't on this first pass is because I have a bunch of 805 parts. So I'm just trying to use up the things that I already have. All right, let's move some of this stuff over here. I mean, this is going to be fun to route because it's going to be tight, but I think we can get everything as is on here. So R7 goes to the transistors, which are somewhere around here. R14, again, is going to go around somewhere around here. R2 is for the RTC, so we'll just put it right here. R11 is for the LED, so that's going to end up somewhere up there. And then JP1 is, man, this section is just, okay. So this is going to be for the RTC. This is for the RTC. This is for the light sensor, and that's going to be U1. It is U1, so that's going to go up here. And then one of the things we got to think about is where does it make sense for these sensors to actually be? Should they be in the center of the board? Should they actually be maybe on the edge? Because then maybe I could make a 3D print enclosure that just leaves only the sensors exposed. We'll figure that out a little bit. So R3, let's put this one here. R9 is for this stuff up here. Let's turn the text. I want, yeah, let's turn that off. Oh, wait, I need that. C1 is going to go for the mic, and the mic is which one? The mic should be like a little square. Is it MK1? Okay. So let's move this like around here. Let's move this to here. Move, route, or rotate. Move this over here, move this over here. So C1 was the microphone capacitor. R8 is for this mess of stuff over here. Our C6 is for the regulator. Man, this stuff over here is just a mess. USB power detection. Okay. Okay. I don't know. I bet we can still get this to fit. Thank you for the follow, eval. Okay. Okay, doke. So, I don't know, man. I think we could make it work. Okay, wait. Let me save this, because I probably don't want to save this after I jack up where everything's at. All I'm trying to do at the moment is, if I really wanted to get crazy and try and get the coin cell to fit, could we do it? The other thing we can do is we can step back and say, okay, we've got a lot of like optional things that I added that maybe we just say they're not really necessary. But you know, I mean, that's part of design is we start with, let's try to get everything we can. And then it's a lot easier to say, okay, let's drop off some of these other things that they're really not as important as, say, making sure the sensors are set up correctly. Like, for example, the USB power detection, it's two resistors, which right now are taking up maybe more space than we need. So we could potentially just drop that as a feature. I mean, there's really nothing that's driving it. I just thought it'd be cool to do it. But now that I'm starting to see this, it's like, gosh, we just created a major mess. Okay, that's not even close. Nope. So close. Yeah. So if it wasn't for the SD card, man, I think we could do it. The more you place things, the more it stresses me out about routing. Yeah, I mean, there's no question. What this is going to end up doing, I'm going to end up doing is the top layer will be mostly traces. The second layer is probably going to be traces. And then the third layer will be power. And the fourth layer will be ground. And then that way I get a nice ground and power plane. And then we can, for power and ground, we'll just via down into layers 3 and 4. But I'm feeling like this is not, I don't see how we're going to be able to do this with, I don't think this is going to be able to be done with 2 layers. Since we're dealing with sensors and with sensors, you want to have a really nice clean power. I don't think I would be comfortable making this a 2-layer board. So the SD card, so Empire's asking about the SD card. The trouble is, okay, first thing, I got to make sure that this is actually the right orientation. But the problem is there's pins right on the edge. So I don't know why they did that, because it really messes up how you can use it. Like, why aren't these closer back here so I could just slide this whole thing off? But Are you going to stencil and flow this in your oven? That's my plan, yeah. It's going to be tough. This PDM sensor and this light sensor I'm a little bit concerned about because these pads are a little bit tight. But everything else I should be able to reflow with my oven. I will end up getting AddOhms stencils to do a metal stencil because Kapton is not going to work well for this. It's just too fine pitch. So, okay. Wow. Yeah, let's actually, while I'm thinking about it, okay, let's do two more things. So, first is I want to revert to, let's just close this, discard changes. It's because I wasn't paying attention to the way that I laid that out. But I did save it before I moved everything around because I was just trying to see, could we even get, yeah. So this at least has a little bit of logic to where the parts are located because the other was just me playing around. Now, what I'm thinking about is you might be able to fit if you switch to 603. Yeah. I'm still okay with just putting the battery on the back. In fact, it has to go on the back because, look, if I was to put it right here, so this is the front of the battery holder. Oh, no, never mind. I'm just thinking about, because I screwed this up on my binary clock on one, actually on my binary clock, I can't remove the battery because of how I designed the battery holder. But yeah, I got to think about how to actually get the battery in and out. And so what this actually means is the area in front of here is probably not usable for components because the battery will have to physically go this way. And so it just more and more feels like it's going to have to go on the back. So same thing, like if I was to even say, put it right here, this wouldn't work because there's going to be pins right here. And if I look up here, this is going to not work either. So it's basically going to have to go on the back and it's going to go like this or something. Or we're just going to drop it. Go down to 0201, then you can put the battery anywhere. Yeah, that's true. I won't be able to solder anything, but yeah, we can do that. What about placing some of the passes on the back? So the battery might cause clearance problems without having female headers on the feather. I'm not worried about clearance. I mean, the battery is only 20 millimeters thick. Just to have pins in here is going to cause it to be thick enough. Again, I'm also looking at this from the perspective of it's an optional connection instead of a required connection. So I'm not even planning to populate it on like the first boards that I make. As far as putting anything on the back, any parts I put on the back, because of my reflow oven, means I have to hand solder them. And so I want as few things on the back as possible, with few being 0. I want 0 things on the back. Okay, let's do, what I want to do now is I want to finish the, okay, first thing I want to do, because we're doing this, I want to see what I want to go back to the data sheet for the SD card reader, because I wanted to understand how the pins are working. So the pins are definitely on the back side. Card goes in the front. Okay. I mean, I didn't really expect it to be any different. I just, man, I guess I get mechanically why they did this, but I can't believe they put these ground pads and then the two chip detects here. I guess the question is, do I care about chip detect? Because, oh man, wait a minute. Oh, these holes are in the, oh, really? Well then how do other boards get an SD card holder? Oh, maybe they, I guess, no, it won't, because it won't fit on the other side. All right. Well, you wouldn't, so TechZ said it feels strange to put a battery in the oven. You don't actually put the battery in the oven. So this is basically, the way this works is, this is actually a metal clip. And so this whole, starting from this corner, you come around to here, and then you come around to here. Oh, gosh darn it. Let me rephrase that. So if you look here, there's like this outline. And this outline is actually a metal, just a piece of metal with two tabs that go down and get soldered. And so the reflow oven solders this tab and this tab. And then ideally you should put some solder paste on the ground pad. And so then that creates a little bubble so that then you slide a battery into the holder, and then the top of the holder connects to positive and the bottom would connect to ground. Yeah, so. Yeah, I mean, if we put the SD card reader on the back, then we would have to, I'm okay with, I would rather have the battery holder on the back because it's going to be easier to solder. What I was just realizing though is these are holes, right? So if this is the width of the hole, yeah, right. So that's the width of the hole. That means these pads are sitting on top of a hole, which doesn't make sense. So does that mean we actually have to? Does the SD card, does this SD slot actually have to come back to like here? Huh. Oh, also notice how they did a cutout? Okay. Huh. Okay. So I wonder if these holes are a different size on this particular feather so that this actually fits. Now you might be saying, well, wait a minute, why are you bothering to put an SD card when there's this feather that has one? True statement. However, if I want to say use my shield or my wing with a feather that has an RF radio, then the SD card slot needs to be on the other side. Then I would be using a feather that doesn't have an SD card slot. So what I'm thinking about is, so let's see, the diameter of this hole is not clearly shown. This is a 0.1 something. And this is a 0.1 something. So what units are these? These must be inches, because it's 2 inch, right? 2 inch is about 50 millimeter. Should be 54 millimeter, right? Okay, 51 millimeter, okay. So what is a 0.1 inch hole? 2.54 millimeter. Can't believe I just looked that up. So what is I'm just going to change one of these real quick. Because it looks like this is a 2.7 millimeter hole, which I guess is so that a 2.5 millimeter screw will fit better in it. But I'm guessing that they had to change it to a 2.5 because otherwise this would not have fit. It still doesn't. So I'm gonna have to look and see if I can find what micro SD card holder she's using, because yeah, that's gonna be a problem. Oh, it's just a holder. Can we 3D view this? Okay. In their example, the pads, yeah, I noticed that too, that on the left side, it's just, it has like ground pads, and on the right side, it's not plated. So why are the first two holes plated and the other two are not? I think it's because they were running out of space. Hey, Starhowl, thanks for the follow. Shift the SD card holder more to the middle. Yeah, I mean, I think that's what they did. So if we come back to the Adafruit picture, so look, I mean, this is actually a really good indicator, is look at what they had going on. They put these ground pads right on the hole. And so if we try, see, I think the problem is I'm using a different footprint than what they had. And so, but I think we would have to do something like this. And then I'm thinking we might want to try to figure out how to do a cutout here like they did, because then I want to be able to get my fingers in there and pull the card out. Okay. I'm starting to run out of steam. And so I think what I'd like to do, I like Babin's idea. Let's see what happens if we throw this in the 3D viewer. I don't know how many of these things have 3D packages with them. Oh, really? Is like, so of course those sensors we made don't have packages. And then I guess the SD card doesn't either. Okay. Oh, do I have ray tracing turned on? I must. Yeah, I do, because let's, okay. That's funny looking. That's not the right package, but that's okay. What width is available for the SD card? I don't know what the, I don't know, good question. Well, that's weird, because actually in the 3D viewer, it looks like we have space. So how does that work? Look at that. We have miles of space for between the hole and the SD card. So I wonder what's going on. I wonder, is that because we changed the size? And then am I just viewing this, oh, I am viewing this wrong. So this is the hole, and then this must be the keep out for for what would have been the ground that we're not going to have. So we actually have a lot more space than I realized. Okay, so we're actually in good shape. Yeah, I think it's just clearance, which makes sense because it's probably clearance for like the screw head. So that's going to be a problem. I mean, or potential problem, but not one that I'm going to really worry about because can't really do much about it. Tech Z, thanks for coming by to the stream. We'll definitely be working on this probably on, if not Sunday, we'll be working on it next Wednesday. Yeah, actually, Babin, I'm really glad you said to look at it in 3D because I still think it's a good move to switch to the 2.5 millimeter. It's going to make putting a screw in there a little bit tighter, but it gives us a little more room, and it means we're actually pretty okay on the total layout. So that's looking pretty good. You know what we should do? Let's every time. We're going to save this so that when I make my graphic for next week, it's okay. Oh, what did I just? I thought that was this. What did I press? Oh goodness. Reload board. Okay, so let's do export as PNG, bald sense PNG, first pass, layout, ray, and then let's turn ray tracing off. And I've got a reason I do that. It's because this is the color I use for the thumbnails. So bald sense, first pass, flat. Is there a better angle? Yeah, maybe we'll do that one. I like that a little better. Okay. Okay, flat, save. Yep. Okay. All right. Yeah, I love that the notes following. Yeah. Okay, so I mean that's okay. I'm optimistic now because I really think we'll be able to get. We've got plenty of room to cleanly lay out the board. I'm not worried about that at all now, especially if we keep the battery on the back. Oh, where did Taz Z go? Because this would be perfect for them to see what I was talking about. Yeah, so and I think this will work. So we'll put this on the back. We'll have it in this corner so that it's a little bit easy to get the battery out. So that'll work. I don't mind soldering that by hand. And then I'll move this back up later. Like I said, we've got to figure out a way to notch this out. I'm not sure exactly how we're going to do that in KiCad yet. And then what I want to do is I want to rethink what we're doing with these sensors. Like I'm still feeling like we should take all the sensors and put them like right on. No. We got to do this different. The SD card slot, I think I'm going to put over here because I want that to be away from radios. And then maybe we should put the sensors in the middle of the board. Gotta think about that. Or I guess I would actually rather have the sensors on this edge over here, because if we're using an RF radio, it's more likely to be over here, but that doesn't really matter because we're rarely going to be taking readings and transmitting at the same time. So I think it makes more sense. We'll probably want the radio to be, the antenna to be exposed. So maybe what we'll do is we'll line the sensors up over here and we'll put the SD card over here and work backwards from there. Hey, Tails to fall. Talus to fall? Do you worry about the battery holder shorting something out on the Feather? Not really. I mean, yeah, it's a little bit high, but yeah, I mean, I guess the one thing I'm going to be worried about is if it's going to come in contact with the USB port. So we'll have to put Kapton tape on it to make sure that it doesn't short it out. But I mean, right now in this version of the PCB, it's either it goes there or it doesn't go on the board at all, because we're going to have to put the micro SD card over here. And I think I'm going to put the sensors over here. So it doesn't really leave me anywhere to put that that battery holder on top. The other thing we might do is maybe I will go to a smaller battery. No external power. External power is going to come from the Feather boards themselves. My idea was to plug a LiPo battery into the Feather and then plug the shield or the wing on top of the feather. So we could do USB through the baseboard. So I think we'll be okay there. This is cool. I'm optimistic that this can work. It's so funny, and Babin, I really appreciate you saying look at it in 3D, because even if we turn off, because it's stuff like the paste layers, the mask. See, I don't even margin, no, courtyards. All these extra things that help you to better place the components really makes this look a lot worse than it is. So I think we're in good shape. The more and more I think about this, I still want to keep the battery, but we are going to drop that to a smaller package. We'll make that a smaller battery. The 12 millimeter is just too big. Which is a shame, because like I said, it's what I already have, but I'm not sold on the fact that we need it. So okay, cool. Let me wrap this up, and then let's go ahead and we still need to do the thing where we're going to add like a jumper for that battery, so that we can decide if we want to power the. Actually, let's just do that one minor thing. Solder jumper bridged. Bridge. Let's do it as open, and we'll just have to always select what we want, because I don't know offhand which way I want this to go. And then, so what we're going to do is so this wire will now become really? Come on. All right, this over to here. Move this to there. And then the two that we're going to get are VBAT. Let's hide this. Can you see that? No, you can't see that. My bad. And then this is going to be VBAT. Okay. All right. And then up here, we'll take this one, put it like right here, go up this way. Okay. So now we have a jumper that will allow us to select at the time of assembly, how do we want to power that? How do we want to power the RTC? And now that I've done that, I'm going to totally change what I just said, and I'm going to default pins 1 and 2. So we got to move these around. So yeah. Move this one over here. There we go. Move this one over here. Because, like I said, so I'm probably not going to connect. There we go. So this way, if you don't, because I'm not going to solder the battery holder on, and so this will allow us to basically save the effort. It'll come off the battery, but if we want to power it from its own coin cell, then you just cut this trace, solder that, and you're good to go. Can we see PCB new with rat's nests on? Okay. Oh, hey, hardware. I totally missed your follow. Thanks for following. Okay. So if we go to PCB, oh, you know what? It's not going to update. Let's go ahead and update this. Let's go jumper. And it should be bridged, OpenPad, bridged. Oh, God, why doesn't that one have the footprint viewer? That's so frustrating. So frustrating. So what we want is this one. What is the difference? This one has numbers. This one has a thing. We're gonna have to go with the one with the thing. Okay. Save that. So then let's go PCB. Let's do update. Cannot. That's fine. Okay, and now we have a PCB. Now we have a jumper. View all. Oh, come on. Okay, ready? Let's save that. Turn rat's nest back on. Oh, it's gonna be fun. So what we'll end up doing, so I think I'm not positive if we're going to work on this on Sunday. Sunday stream, we might actually, like I said, we might play around with the trivia because it's going to be a relatively short stream. But when we do come back to this one, there's a couple of steps that we're going to do next. So the first thing is we're going to, I'm going to look into see what battery size I want to get. And so I'll probably go to an even smaller coin cell. And then I want to put my sensors over here and put my SD card over here, and then better lay out like this section for the regulator and well as the battery, the voltage measurement, and basically get a much cleaner look at where the parts are going to go. And then after that step, we'll probably reassign what pins we're using for the various signals, because when I put this together, I didn't think about at all where the parts were going to go. And so like if we put the sensor, say over here, and it's connected to a signal over here, that won't make much sense. You know, we'll just kind of clean that up, and that'll make routing a little bit easier. So so maybe we will do those steps on Sunday, because that'll probably take us about an hour and a half to clean it all up. And then that gets us a lot closer to actually laying out the traces. So yeah, so I think that's what we'll do. All right, so save that. I'm gonna close this. Take one quick final look at that. That's looking pretty good. I did want it to do this because, I copy that because I want it to go to, so let's close this, and then let me open GitHub. Let's do repository, show and explore, because I want to go into my README, and I just want it to add sensors being used, these. And then let's do 4 more information. All right, let's save that. Okay, none of the backup files are coming. I'll go ahead and let the PNGs go. I don't really care. Okay, so let's do initial PCB layout, footprint placements. Thank you to everyone in the live stream chat. Commit that, push. Okay, and then I'm not going to create a pull request yet, because what I did is I created a development branch. Let's do repository, view on GitHub. Babbitt. Oh God. Yeah, that's looking pretty nasty. So just FYI, and this will show up over on in the Discord as well. So remember, if you want to keep the conversation going, we do have a Discord server. So there's a link that'll redirect you to the Discord. I would love to see all of your happy faces over there. So my plan right now is I will probably stream on well, not probably. I'm scheduled to stream again on Sunday. Not positive if we're going to work on this or do something else. I'll give it some thought over during tomorrow. And then I'll be back on Wednesday and next Friday. Hopefully by next Friday, the lab will be more set up, and maybe we'll even do some soldering and get back to like video game stuff, because I like to work on video game systems on Fridays. Normally, it's just I'm still unpacking from my move, so I haven't had a chance to do that. So thank you to absolutely everybody in the chat. You guys are extremely helpful. I think you asked really great questions, really caused me to think a few things. I always think it's funny when I see a question and I think I know what the answer is going to be, and then as I start to talk, I realize, oh wait, I didn't consider something. So that's always helpful to me. So really appreciate the help. Everyone that's new, thank you for following or subscribing. If you are over on, by the way, if you are over on YouTube, I'm very close to not live streaming to YouTube anymore. Once I get everything set up and I'm back to my editing, can get back to editing, I'm going to be putting edited versions of my live streams on YouTube, but I'll only be streaming to Twitch. So if you're on YouTube and you like the live streams, I would recommend that you consider following me over on Twitch so that you can continue to do so. Probably be about another month before I make that switch. So thank you to everyone. Again, thank you. Now, before I sign off, which I can, oh yeah, I can move this over now because you guys can't see it. Let's see if there's anyone doing anything that is STEM related on Twitch. Usually by this time at night, there isn't, but I do like promoting engineering and science and stuff. So let's see if there's anyone I can send you guys to that would be interesting. I'm gonna say no. I'll tell you what though. I will say at least that on Twitch, go and look at in my description, because I have a bunch of STEM, science, technology, engineering, math, streamers that I'm following that I think you might enjoy to follow as well. So thank you to everyone. Yeah, the problem is, I'm gonna look one more time. It's just everyone. The only people that are streaming right now are. Wow, that was weird. I was not expecting to hear my own voice. Yeah, I'm not going to. Okay, no, because that's not even related. Yeah, we're not going to raid today, but I will say thank you again for everybody that came by. Come find us in Discord, and it'll be let's keep the conversation going. So have a good night or day wherever you are. Oh, come on, really? That's not working? Jeez. What are you trying to... Oh, God.